here in France. We are supposed to be live streaming, so I think for those of you who are watching this from a distance, well, I want to welcome you as well. My name is Jan, and I am in charge of the Scilab business unit in ESI Group. For this first presentation, I want to welcome everyone to the Scilab community. For that, I would like to go through a brief history of Scilab. It is a story about software and science, but above all, it is a story about men and women. This introduction in the beginning is about thanking everyone who made this event possible. I want to start by thanking ESI Group for organizing this Scilab conference, in particular Laura and Gaël and Aurélie, present here today with us. Good morning, Laura. And I also want to thank Mozilla Foundation, in particular Sylvestre, who used to be part of the Scilab team. And thank you for inviting us in this wonderful location in the center of Paris. Finally, I want to thank all of you for being here, especially the speakers. Here, as you can see, we have a very full agenda today, and so I'm delighted to have you all here today. Let us shortly go back in time. What you see on this picture, it is the last community event we had in France in the very same room. It was in 2015. So, this is a short summary of previous episodes. It was a very successful event. The three best presentations of the event were based out of the votes of the audience. In the first place, the French Nuclear Agency, CEA, presenting on their migration from MATLAB to Scilab. Second was from our Italian partner, Evidence, on state machines with Scilab and Excos. And the third one, from the French Space Agency, we have them today again. So Alain and Thierry, you will be presenting further some space missions. Today it's Mars. Last time it was about landing on the comet. It was a very successful event, and we had every year before this one, user conference called ScilabTec since 2009. They were organized very professionally by Julie, who was in charge of the communications in the days at INRIA, the French research. But I'm not going to lie to you, the last 3 years have been quite challenging. Even though Scilab goes back long time. Its origins are coming from the 80s and the 90s. And its expansion goes far beyond our small team. So here is a short timeline of the three main steps, I would say, of our history up until today. Now I want to go through this short history of time with you. First, Scilab started formally in 1994, and its premises are going back to the expertise of INRIA. INRIA is a French research institute for computer science. In this research center, in the Paris area, we had a team of giants, as you can see in this list, who paved the way for a large scientific project. I was lucky enough to meet two of those giants, Serge, who some of you might know, he was presenting at the last Scilab conference, and Claude, who operated the transition from INRIA to Scilab Enterprises. In 2003, there was a first Scilab consortium whose goal was to drive the roadmap of the software. Those are the founding members from the French elite. And since 2008, our goal was to industrialize the development of Scilab, to conduct a transition from the research to a large industrial adoption. A new generation of computer scientists took over the development of Scilab. Today we have some of them, Clément and Antoine. Antoine, who's the architect of Scilab and our oldest team member, will be joining us. He's been around for 10 years now. So thanks to those talented software engineers, we were able to make a solid and robust software. I'd like to remind you that 2008 was also the first version of Scilab 5. Today we are at Scilab 6. So as the industry was starting to adopt Scilab, there was a rising need for services around the open source software. And it was the very reason for the creation of Scilab Enterprises. The whole development team switched over from INRIA to Scilab Enterprises in 2012. And we soon figured out that from the expert usage to the development of application, our main competitor was actually not MATLAB, but it was rather Excel. So we figured out that lots of our main users were packaging together data with algorithm and developing on top a graphical user interface in order to develop what we call application. This is also what led us to Scilab Cloud, to a new technology and an underlying business model for the deployment of application. It was in 2016. And today you will see a presentation from Sanofi, from Jean-Pierre, about the very first industrial use of Scilab Cloud for energy consumption in the pharmaceutical industry. But around those times, we also had very important research projects which were enabling to develop Scilab further. I'll quote just some of them. Colloq was led by Cédric in our team, and it was to stay close to our friend in HPC, high performance computing. Another very important and major project for Scilab Enterprise and for Excos was Argo, and it was brilliantly orchestrated by Clément. Today you will see two presentations, one from the German Aerospace Center on control system for flight simulator, and just after my presentation, one from the Fraunhofer Institute, the very same Fraunhofer Institute who invented the MP3 technology next to Nuremberg. And today they will be presenting you image processing. There's even a demo backstage. One last research project that I wanted to quote is Megasif. It was a very first taste for us of what is finite element analysis and the development of reduced order modeling. It was a foundation for our future as we got closer at this time already to ESI Group. And from that time on, we also saw a new generation of promising engineers, Hughes, who's with us today, who has a strong expertise in the domain. So if you have questions, don't hesitate to ask him. And you will see also a presentation from one of our partners, Bertin, later today, from Sophie. So it ends up with the question, why ESI at the end or the beginning of this journey? Why did we join ESI? So to give you some perspective about the simulation and analysis market, it's a $6 billion market, and it's quite strongly concentrated. As you can see, there's just a few players that are taking it all, basically. ANSYS is number one, and closely behind, you can see that MassWork is also leading with close to no competition at all, almost. But in both cases, there's a very strong academic footprint, and it creates a natural barrier of entry, unless we have a value proposition that is highly disruptive around open source and that can challenge this status quo. So who's ESI? In a few slides, I'll try to introduce you to this pure player of the simulation market. What is smart virtual prototyping? The differentiative proposition of ESI is to go from analysis, simulation of simple physics, thermodynamic, structural analysis, and so on, until virtual testing, taking into account the manufacturing effects. And this is what produces a virtual prototype. Now, the next step now for the future of ESI, and it's also the reason why ESI acquired Scilab, is to go to smart virtual prototyping, meaning that it's not good enough to have an analysis of the product conception, the design phase, and engineering, but it's very important to see this product in operation, in service, and to assess its performances all along the product life cycle. So this is a short overview of all of the technologies that ESI is developing around 3 pillars: engineering, manufacturing, and in-service. And early on, since 2012, ESI already showed an interest for open source through the acquisition of the OpenCFD team developing the OpenFOAM software for CFD, for computational fluid dynamics. So this acquisition goes along with this strategy of building technologies, and not only product, but also services around solutions. As a summary, today ESI is it's not that big of a company actually. It's around 1,200 people worldwide, but it's fairly largely spread all around the world. And it leads me to the last part of my presentation on Scilab all over the world. So I started to work for Scilab about 5 years ago, and in the first place, I was supposed to develop the business in Germany. We organized, with the help of Jürgen Koch, a professor in the area of Stuttgart, a Scilab conference at that time, and some of the people that were presenting will be here today also. You will have a presentation from Hochschule Esslingen today. We have very large activities at the moment in Japan. As you can see on this picture, there's already a strong competition happening. And well, we had a first meetup with a small group, a small representation of the community last year already, and I actually just wrote this presentation on the plane back from Japan. So India is also a very large user of Scilab. Just simply in the academia, I want to thank Kanan Mugdalia from the IIT Bombay, who has been spreading the use of Scilab. Thanks to him, you can see on this chart, there's around 240,000 students that were trained with Scilab. It is actually more than Python in engineering school. So here, this is the spread over the years. And this year, in August, we had a conference in India, and this is Professor Kanan Mugdalia presenting around the open source supported by ESI on OpenFOAM and Scilab. And obviously, friends, we won't forget our roots. There's a very large community, also lots of academics. Every year, there's around 30,000 students from preparatory classes, from engineering school, from the university that are learning Scilab. It produces sometimes some funny results. When I have a look at the social networks, sometimes I stumble upon such funny tweets. So this is also the new generation speaking, I guess. And in the US, well, the US is it's a bit difficult, to be honest. I would say it's MATLAB land. But something funny happened. It was in the beginning of 2017, as we were joining ESI, and we saw this post So we decided to contact John, and yeah, I'll tell you a bit about John. So John Eaton is the member of the Resistance, I would say. It's a founder of Octave, and those are a few slides from him on Octave. So why the name Octave in the first place? It was a reference to a professor who passed away last year, and those are a few, in a few lines, the origin and the history. Actually, Octave started out as some sort of a textbook companion on chemistry, because John at that time was studying chemistry. Well, the first release, 1994, might sound familiar to you. It's the same year as Scilab. In 2002, the book that was supposed to go along the software finally was published, but well, the software was already growing and in a direction that surprised John in the first place, because it did not intend to make a clone of MATLAB at the first place. And so, if you look at it, this is the scope of the project. So this is actually a photo from John. He highlighted all of the functions that he found in the first manual of MATLAB, and he was just trying to, implement all of them. And he thought at that time, well, it cannot be that hard, Look at it. Well, now it's a bit more challenging, I would say. So it made us also meet new people. And here today we have Botao, who will be presenting, coming from the US. So thank you very much for coming all the way, on the use of open source in an enterprise computing environment. But let's go back to Scilab and the usage throughout the community. I have a few slides, 3 slides on some statistics here. This might interest you, just to have a look at the different application field where Scilab is being used. Those data are coming from form. When you download Scilab, you can fill up a form. You don't have to, but you can. And here we have a sample of around 100,000 downloads that filled out this form. So in the first place, there's a lot of users using it in electronics. Second is data analytics. And mechanics is coming in number 3. Now, in terms of domain, including the education, as you can see, education is very strong. So 63% of our users come from the education, and the rest is industry. And those are the different industrial domain where Scilab is being used. So research is in yellow. It's very strong also. And afterwards you have a lot of different fields. So I'd like to conclude this talk to now talk a bit about the future of Scilab. And here I'm actually adding a graph that is coming from a feedback of a teacher. He has been using Scilab for 15 years. His name is Klaus. And those are the kind of things that give me motivation to keep investing efforts in Scilab, to see so much things produced by the community. Now you might wonder, where are we going? And this is also the purpose of the final talk of today. But here in one slide, I'll try to sum up our strategic targets for the future in terms of who are we going to aim at. In the first place, obviously, we will want to bring additional value to existing traditional simulation user. Here, making a competition to ANSYS and not MATLAB directly, but trying to bring in different domains such as CFD, so computational fluid dynamic, some model reduction technique, in vibroacoustic, bring some optimization. Those are some of the projects that we've been doing in the past 2 years, and some system model deployment. The second target is obviously system simulation engineers, so in competition with MATLAB. And here our value proposition is to embrace open source, to unlock the engineering productivity that goes along with it. So if you have additional resources that will join your team, well, you'd better off using an open source software that can scale with your engineering needs. And obviously, in the automotive domain, model-based design is big. In the signal processing, also for chip design, as you will see later today, there's a strong need for that. So in both domains, whether it's control system and block-based diagram or scripting, this is something where we want to grow bigger. And the last part that we don't want to forget is about application developers and to provide them as a, well, I said competition to Python, but really is there a competition when we're talking about open source? It's mainly to bring and discover the potential of simulation, what goes around mathematics, optimization, statistics, signal processing, and control system, to bring all of those value to fields that are new to the simulation, mostly. So if you look at some of the presentations that we will have, for instance, from Sanofi in the pharmaceutical, this is a field that is not as mature as aerospace and automotive. And we also have lots of examples in process industries, for instance, in risk modeling. So those are domains where there's a very large potential to enlarge the use of Scilab. Thank you. So without further ado, I'd like to call upon stage the next presenter, Michael Schäuberle. Did I pronounce it right?
Almost.
Doctor engineer from the Fraunhofer Institute for Integrated Circuits. He's the head of the group for imaging solution. Dr. Michael Schäuberle. Schäuberle?
Yeah, great.
Okay, it's received a diploma in electrical engineering with honor in 2006 from the University of Erlangen-Nuremberg. He then joined the Fraunhofer IES and started to work on high-quality imaging systems in the electronic imaging department. In 2007, he joined the University of Erlangen-Nuremberg to continue the research on algorithm for high-end camera system in a close cooperation with Fraunhofer IES. In 2013, he received a PhD with honors in electrical engineering for his work on digital cameras. After working as a chief scientist in electronic imaging, he is now head of the group imaging solution at the Fraunhofer IES with a focus developing and implementing novel imaging technologies. His motto, beyond human vision. That's nice. So we are ahead of schedule. You can take your time. You have 30 minutes.
Okay. So welcome from my side as well, and thank you for the introduction, Jan. Just to give you a little background where I come from. So Jan mentioned already from Germany, from Erlangen, and I come from one of the Fraunhofer Institutes in Germany. This is an applied research organization, if you haven't heard about them yet. Altogether, it's around 25,000 people, and our institute is one of the larger ones with around 1,500 people involved altogether in this institute. And in this institute, we have many different fields, and the group that I am heading is focused on imaging. So we're doing imaging technology. It's not that much about processing the final image, but about making images, generating images. And that's where my motto and this topic comes from. The idea is to do something that is beyond the human eye, to go further and see new modalities, new technology, and new things that are out there in the world. Today I will talk about the topic polarization imaging. That is something that people might know if they have photography and turn a polarization filter to suppress reflections, for example. But polarization is so much more in discovering new properties of materials, of analyzing materials, and in a close cooperation with Jan and other partners from the Argo project, we can now present a result where we can go through the whole chain, starting with Scilab and going all the way to an industrial application. This is work from people of my group today. I brought two colleagues, Koray and Stefan, are also here in the audience, and they can later show you the demo. So this is the green one lighting, green glass over there. I hope you will understand what's in there throughout the presentation. I will talk firstly about polarization of light. So what is behind that? What does that involve? It might be familiar to some of you if you studied physics. In other disciplines, it's maybe not that common to know about that, so I will give a brief introduction. I will show how to measure polarization, how to derive values from that. I will show how we do algorithm development and show the final product or the final chain of what we developed, going from the development to the product in the Argo project and with a demo, as we've seen over there. And the application of the image you see here, this is a drinking glass. This is a special type of drinking glass, and we are looking at the stress in these drinking glasses as one example. More on that later. Let's start with at the very beginning. Light is an electromagnetic wave, and light has a certain property. For example, the amplitude of this wave. This is something we perceive as the brightness of light. So if there is more, then we could draw a wave with higher amplitude. If we change the wavelength of light, this is something we perceive as color. So red or blue is simply different wavelengths in light. And this electromagnetic wave has another property. It's the orientation of the waves. And this orientation, this is something that is mostly not visible to the human eye. And this is the effect of polarization. In typical light sources, mostly the orientation is equally distributed. So have waves of all kinds of orientations, and this is something we describe as light that is not polarized or has a degree of polarization of 0%. If we pass the light through some effect, we will see later, it's possible to get light with a very strong orientation or very high degree of orientation. And we describe this as a degree of polarization of 100%. So most or all of the light rays are polarized in a certain orientation. There's something in between, so you could have partially polarized light. You could indicate this by having many in a certain direction and some in the other directions, for example. And we could also measure, on the last line here, the dominant angle of the polarization. So we can say, oh, it's polarized horizontally or vertically or at any other angle you would describe. And the first question comes, where does this come from? Why do we have polarization? What is the effect? If we look at natural light sources, let's say the light from the sky, the light from a light bulb, from a fire, all of those light sources are unpolarized. So all the directions and orientations are present in that kind of light. The only exception is that in lasers you have polarization by nature or by how it's generated. But if light is unpolarized, why do we talk about it? There are many effects that can cause the light to go polarized. So, for example, if you have reflection on a surface, let's think of a water surface, if you have a piece of glass that reflects the light, if you construct a beam splitter that splits the light into two beams, this is something that gives you polarized light. So on the right you see the example of a surface with different refraction index, and the incoming light from the upper left is split into two rays of light, and those rays of light are, one of them is horizontally polarized and the other is slightly polarized. So this gives you a strong polarization simply by looking at a reflection of a surface. In nature, this is something that is, for example, in water, very important. So some insects are able to look for polarized light, fly there and try to lay their egg there. So they see the polarization, and try to detect water bodies and to lay their egg. So they're not trying to find the color of water or the shininess of water, they are simply looking for the degree of polarization in nature by flying around and then laying their eggs where the polarization is high. We can use this, for example, in surface inspection. So if you want to have a coating on a surface, want to have flatness or something, this is something where this effect could be used. And this goes much further than just polarization. It's a whole domain of ellipsometry, analyzing the reflections. There is also something that reflection at non-metallic surfaces. You have something at the human skin, that is at plants, at plastics, and this is something that can help in object classification. So if you want to sort something, if you want to detect different parts of a plant, for example, you can use this effect to classify or to help classify and use this as an additional modality to segment a plant, for example, in image processing. Another effect that causes polarization is nanostructures. So if you have something that is structured in the range of the size of wavelengths, this can create polarization. This is something that is used in transmission or in reflection as well. So let's say if you want to create polarization filters, there is one type of filters where you have a wire grid. So there is small wires, so to say, in the order of the size of the wavelength, and those cause the light to be polarized, so polarization filters. There is another application that we found that is the inspection of carbon fibers. So in carbon fibers, this is also very fine conductive material, and this material causes the light to polarize. So I shine unpolarized light onto my fiber and I get back polarized light. So the setup you see in this image, this is simply a ring light that shines down onto my surface and a camera looking down at my object. And if I do this with regular imaging, I would get an image like this. So this is a woven pattern of fibers. So it's a bundle of fibers interwoven with another bundle. And this is a prefabricated material, like a fabric, that is used, for example, if you want to fabricate some components, let's say a rotor blade or a car component. Then you take these fiber cloths, fabrics, and put them on top of each other and press them together. And what is important about those is if you want to look at the strength of a material, then in carbon fibers it's very dangerous if those orientations are wrong. So if they're wrinkled or if they're shifted or distracted, then this causes the strength of the material to go down. In car parts, you also have the problem that if you want to have this as a surface, the customer pays quite a lot of money to have a nice surface. So you want to make sure that the surface is nice looking and regular and symmetric. And if you would start with an image like this and wanted to do image processing to check if this is properly oriented, you would have quite a hard time because this material is black from its beginning, so it's not easy to do imaging with black material, and then lighting it is very difficult because you get a lot of reflections, and finding the orientations of fibers, I would say in this image it's quite challenging or even impossible to do that. If we take the same photo or the same image with polarization, we would have another modality to work with this image. And this modality would give us something like this. What we encoded here is the angle of polarization, so the angle of the light that comes back from the fiber as color. And this image is enhanced with color, and we can easily see that the fibers in this case are not closely together. So in the spaces between those, there are gaps, and they would not even be, you cannot observe them, or very difficult to observe the gaps in these cases here. And this is very easy to be done with polarization. So it's a quick inspection that helps quite a lot. I didn't do anything. Okay. In inspecting carbon fibers, for example. There is another effect that is the scattering of light at small particles. So this is another effect that animals use. The particles in the sky cause the light of the sky to be slightly polarized, and this helps some animals navigate and fly in certain directions. But this is also for particle analysis in the scientific sense. The effect is that the light that is reflected from a particle in a right angle, this is fully polarized, and light that is mostly the same direction that goes on unpolarized. So another effect that causes polarization. Another effect is the birefringence in optical anisotropic material. So it does not have the same optical properties in different orientations. And this is a material, for example, there is some quartz material, some calcite, some stones that exhibit this property, and they cause the light, after passing through, to be split up into two properties, two rays of light. This is an effect that is also present in glass and plastics. So in transparent plastics and glass, the light will change its property if it goes through, and will have different polarization properties afterwards. And this is an effect that we are using in inspecting glass. So what we have here is an example similar to the setup we are showing back there. The idea is you pass polarized light through the glass, and the glass is able to modify the polarization of the light. And after that, you can detect and measure the polarization and directly see, for example, areas of stress in this glass, where the glass did not cool properly or did not cool as intended. And these areas can be identified, and the glass can then be checked if it's good or bad, so to say. So to give you an idea, with polarization, there's many fields that open up and that can help you do more than just looking at the things. It gives you more information about some objects around you, and this is a method we are using and working on and trying to extend. So how do we measure polarization? The basic principle is we have more degrees of freedom in polarization, like at least 3 or maybe 4. It's not just the intensity, as I mentioned, but it's the degree of polarization, the angle of polarization, and there is the intensity of circular polarization. So it's 4. Right now we are using 3. That is sufficient for many applications. And for doing this, you need at least 3 or 4 measurements to do this. And the most basic way is to use a regular camera and use a filter in front of the camera and simply make 4 images by rotating this filter. Basic principle. This is not really nice because you can do that if you have the time to do so. If you want to go to an industrial application, it's maybe not the best idea to do that. You can do that quicker, not rotating, but doing electronic shutters, but that has its own problems with temperature drift. You can do that with side-by-side cameras, using 4 cameras with fixed filters, for example. And there are many different variations of doing that. Having line scan cameras, so if you have an industrial process on a conveyor belt, you might use multi-line cameras to scan polarization. You might use something that uses beam splitters, so one optical path as the image shows, but with optical beam splitters, that makes everything quite expensive. But those are solutions that were available in the past. In the last couple of years, we've been working on one approach that we call the division of focal plane. This is an approach that is very similar to how most color cameras work today. You simply have one pixel that is sensitive to one color, let's say green, and the next pixel is sensitive to red only. So you treat in some spatial resolution of the sensor for getting another dimension, let's say color, or in this case polarization. And the image on the top right shows where you put on polarization filters, like for the analysis, and one pixel has the filters with this orientation, the next one has this orientation, and so on, going through all of those pixels. So the camera in the end will have smaller resolution than a native black and white camera, but it will have all of those properties in there. And to do this, you could glue on such a filter to the sensor. That's maybe for a first test. This is not practical for small pixels, for modern cameras. And the idea is to use nanostructured filters, embedded them directly into the CMOS fabrication process. So on the bottom left, you see such a pixel design from a couple of years back, where you have these nanowires as polarizing filters directly embedded into the pixel design. And if you build such a sensor, that's what you see in the middle, and make a camera out of it, you have a camera that is able to measure polarization in just capturing a single image. And that's how we started and how we developed this technology. And we are in the lucky position that we found something very interesting that big players are now catching up to do. Sony has released a polarization sensor with 5 megapixels. So even if the native resolution is 5 megapixels, take something away of that, it's still enough pixels left to work with that. And for those sensors, we are seeing cameras to appear from most camera manufacturers. Some of those cameras we have already working and have them in the lab. Some are only announced so far. And we brought one of those new cameras, in this case it's a Chai camera, with us. And we had a head start to work with those. So we have software and algorithms and have been working on those to go further. So what is necessary? What is the challenges you need to do with that? What is necessary to do with those cameras or with these images? First of all, you have, as I mentioned, the pixels side by side. So one pixel is sensitive to this orientation, and the next pixel is sensitive to a different orientation of light. And you need to do some processing to reconstruct a full image. And this is something that has been solved in color imaging for doing the debayering, the demosaicing, color reconstruction. But in this case, the problem is slightly different because the correlation between the channels is different from color imaging. So that's something you need to solve as a challenge, how to process this raw image. There is not much research on that. There is not much standards or established algorithms for this. Next challenge is, how do you calibrate those cameras for measurements? Right now on the bottom right, this is a colorful image, but in the end you want to do measurements. You want to put a number to it and you want to say, this has this much stress in the image. So you need to go through the whole chain of calibrating the camera, the raw data, make it stable for temperature, and produce a final image or final measurement results. And what we are currently focusing on is, in the beginning I've shown many different applications of what you can do with polarization, and what do you need to actually make this image good. So you need to have a certain arrangement, a certain kind of illumination, a certain kind of combination of filters and lights, and this is something that is very different from one application to another. In the end, the user is usually not interested in saying, oh, this is a degree of polarization of 25%. The user usually needs to have some classification. He needs to know, is this a good or a bad glass? Is this something to get a measurement in the end, not the polarization value. So there is much more processing involved to get to an answer for the customer. We started in algorithm development in the Argo project, or before the Argo project, but also in the Argo project. And we analyzed different ways of doing the image processing. The idea is we wanted to evaluate different types of calculations, different modes of working with the images. And we did this in the following setup. In the beginning, we just used a regular camera on the top right, just a regular off-the-shelf industrial camera. We had a rotating motorized filter on the camera to do the sequential measurement. And for example, on the bottom right, this is a light source with a polarization filter, a glass on top. And we started using Scilab for this, and there were two challenges. The first challenge was that if you take an industrial USB camera, that is something that is not supported right out of the box. So you need to extend to get industrial imaging live into Scilab. And this is a module we worked on. We worked on for one camera type, And what we were able to do is we were able to capture live images and do a live processing of industrial image camera, go into Scilab, do processing, and display the results. Another module we wrote in this case was to control the motor. This was a step motor controller to interface it, and with those we were able to have an interactive demo setup. Looked very similar to this one, where you could tweak and turn around and hold the glass in different orientations and get a live image to work with this. And this is an important step because if you make one image and then you go to the processing and type in something, and let's say even 20 seconds later you have the result, it's very hard to tweak and turn around your setups and modify. So getting to the interactive workflow was a very, very major step for us to analyze objects. So you have to imagine you get a sample from a customer, it's some object you have never used before, seen before, and you want to see, is there some defect maybe here, or if you turn it like that or that. So it's quite a step of sitting in the laboratory and working with those objects, and an interactive working is interesting here. The processing we implemented is something we take like the 4 raw images from the camera. There is all of the calibration, the calculation procedures to get to the Stokes parameters, so the first defined set of polarization description, and then go further from there, let's say to calculate retardation in the glass, magnitude of stress, orientation of stress in the glass example. The demo I will be showing over there is then the next step, how to get to the product development. And in this case, we were very lucky to have this Argo project, as mentioned, and with this combination of tools, of partners, we were able to have a very nice chain of going from the algorithm development to the product. The idea is we are using and integrating these upcoming industrial cameras. It's a 5 megapixel sensor, it can do single shot imaging, so this is something that is industrial grade. You can put it on the industrial production floor and it will withstand the conditions. There is somebody to replace the camera if it breaks, you can simply buy a new one or replace it quickly. And they have a high frame rate to do inline inspection. So if you go to, let's say, glass production, that's something that they're doing, let's say, with 5 per second. So 5 objects per second racing by, and you capture 1 image each and make an image of that. What is lacking with these cameras right now is the software. So they have some software to do colorful images, some of the manufacturers, but what you still need is an extension and plugin, a module that is able to give you some measurement values. And what you want to have is a calibrated measurement, for example, of the retardation. So how much is the light retarded or delayed going through the glass? And this is something that you measure in nanometers, and this is something that people working with glass are familiar with. So they want to have this number, and this is something that needs to be calculated and calibrated. And what the demo shows, what we are doing here is we are able to measure the magnitude of retardation, so how much stress is in this piece of glass, and we are also able to measure the orientation of the stress. So in which direction in the bottom of the glass is the stress oriented. I mentioned the Argo project. From doing that, going from Scilab to a DLL to a product, one solution would be to reprogram everything again. That's not what we propose, what we should be doing. We were very lucky to join this Argo project, and I would like to give you an idea of what we have been doing, what the whole consortium has been doing there. It's WCET, aware parallelization of model-based algorithms for heterogeneous parallel systems. That's quite a lot of words in this title. WCET is worst case execution time. So the idea is you want to make sure that you have an algorithm and you go to the next step in modifying that automatically, that it guarantees you real-time performance, hard real-time performance. that you can be sure, no matter what happens with the input, you get a defined output at after a certain delay of time. And this is something that the compiler tools that have been developed with the partners here are able to do. Then the next step is, in this project, it's a transfer to parallel C code. So you put in some code, it can be Scilab, it can be other code, and it goes to a parallel implementation of your program. So it gets distributed around multiple cores and still ensures that it's real-time capable. And it is able to use parallel architectures, let's say CPU with multiple cores or some other types of multi-core architectures in the FPGA, for example. It's a project that is still ongoing, but almost finished, and we were able to use part of this tool flow here to work in this idea. As I mentioned previously, we started with the Scilab algorithms for processing the raw images. We had them implemented and we're using them, and we used one of the tools here. This is the MTrix Parallel Studio that goes from a first step of making your Scilab code into a C program. And this is part of the Argo, so Argo works on that and refines it and even optimizes and optimizes. That is not yet included here, but at least the first step is included here. So the algorithm automatically is converted into C, and this is compiled together with Visual Studio into a DLL, and this DLL is then included into Halcon. Halcon is a software that is used in industrial inspection scenarios. So let's say if you have something on a conveyor belt and you want to inspect some object passing by. Halcon is one possible way of doing this. It interfaces to an industrial camera, gives you the image, gives you tools to work with those, and allows for real-time deployment in the factory. So by providing tools. And what we are showing back there is the demo of starting from the Scilab code, going through all of that automatically, and finally putting the result directly into Halcon. It's not without manual interaction, so you need some interface code to go with that, but the algorithm itself goes through that chain. And I think this is a major step forward for us, because if you're in research and development, you're constantly trying to modify the algorithms and changing this, changing that, and it's much easier to do that in Scilab than to do it in C. So what we provide finally as a result of that is a software as an Halcon extension that can be used with all industrial cameras. So we don't care which one it is in this case. It is able to calculate the polarization values from the raw data of the camera, and let's say the degree of linear polarization, angle of maximum polarization, Stokes values. And it goes further in the example we will be showing here. It's the glass parameters, so retardation, magnitude of stress, orientation of stress. And the demo we have there, it's similar to this one. It's a light source, a polarized light source. We put the glass on top and have a camera on top. The camera goes into the PC and does the processing and shows the result in real time. So I would like to invite you afterwards at the coffee break maybe to have a look at this, how this comes together and how we are using the whole process. In this demo, we are processing the raw image. We are getting to the intermediate Stokes values for polarization, and then calculating the glass values afterwards. That already concludes my talk. I was talking about polarization imaging. This is a modality that is quite new from my perspective. It's known in physics, but it's not really known in the applications yet. So it's something that is upcoming, that is coming to more and more applications. It requires quite a lot of application-specific tuning and processing. So it's not easy to go from one to another, because quite a lot of those is quite different. And as a summary, the last part is the Argo tool flow, where you can go from Scilab to software that is coded or implemented, and in this case, even up to the point of product delivery So that is something that could be used in an industrial context, as we are showing here. Okay, so that's it from my side. Thank you for your attention. So, maybe question, quick question?
Yes, actually, I was going to propose that. If anyone has a question, Butter?
So in real industry, the measurement result is something where you can sort out the glass. So if you detect that something has gone wrong, you can throw away the glass and only pass the next glass. And this is done for many aspects, like if there is a bubble in there or a stone, then you discard the glass. And this is a process that is, so discarding the glass, that's what they know and what they're doing right now. And this is simply another modality they are testing for. So it goes into an inspection machine, and after the inspection machine, there is a pusher that throws away the bad glass. Based on a threshold maybe, or on some other metric. Mm-hmm.
How do you see the incoming? How do you see the perfection that could be made with ScilabTec?
So I have not been dealing with rocks lately yet. So there is some disciplines that know polarization for quite some time. So that's the life science, biology, mineralogy. They have polarization in their microscopes. And that's what they have. And I don't think this technology is improving that much. But we've had people discussing the idea of mining, for example. If you're mining or having large amounts of rock, so to say, and want to sort them or want to detect something in them, polarization can help and go forward. I'm not sure if there is a direct request to Scilab to include polarization right now. I think the major challenge is that if you have an industrial camera, it's going to be hard to interface it, to put it in there and get it into a live workflow, to put it into industrial production and have everything go through Scilab. I think that's not that common yet, maybe.
I think, yeah, the three aspects that I would see here as a benefit for a larger audience is, first is image processing, I mean more traditional, I would say, not so specialized, but for everyday purposes, I would say. So image processing is the first, as you mentioned. There could be some improvement in all of what goes around classification, maybe all of the machine learning algorithms that could come and enhance those capabilities in image processing. And the last point that you mentioned is also connection to the hardware. Mm-hmm. So that would be, and that's also one of the things that you presented in your presentation. So yeah, okay. I don't know if this helped you in any way for geology. Okay, thank you, Michel.
Okay, so thank you.
So our next presenter, Stéphane Jiménez, doctor. Wait, so that I can shortly read your introduction. So, Stéphane, you are working at ArcelorMittal Global R&D as a project manager for digital knowledge management. Your current project and activities, you've been working for 9 years at ArcelorMittal, design, implementation, and management of the Diabolo solution, so that's what we will see today. Exploratory project, scientific computing, and digital knowledge management. So it sounds very relevant to our subject. Your education, you have a PhD in computer science for physical modeling and simulation of complex deformable body, 1993. And you worked at the laboratory Leibniz previously LIFIA, Laboratoire Informatique Fondamentale et Intelligence Artificielle. And you graduated from Grenoble INP, Institut Polytechnique de Grenoble. So Stéphane, you have the stage.
Okay. Good morning, everybody. So I will tell you the story of what we call Diabolo. In fact, the title is not on this first slide, so I will pass to the second. What we call Diabolo, which is the global framework we set up in ArcelorMittal R&D for support and manage the full life cycle of scientific models. And in fact, I'm here because we choose Scilab as a pillar for this global system, and we will see how Scilab has been fully exploited for the main component of this framework, but also to distribute and reuse model in factories. So near 10 years ago now, some people involved in knowledge management in R&D in ArcelorMittal decided to tackle with the problem of the poor management of model life cycle. The fact is that a lot of R&D models have developed, numerical models are developed in R&D for 30 years now. These models are very heterogeneous in technology, in structures. They are developed by people geographically distributed. And these models are used and maintained by many different users over the years. The result is that they are not easily shared nor reused. They can be instead redeveloped, partially redeveloped. And the model life cycle is very hard to manage. In fact, we constate loss of knowledge, of digital knowledge, and we have a huge time from conception of the model to industrial use of this model. So we decided to tackle with this situation and trying to develop, to set up a whole framework to ease the model sharing and reuse, to ease training and use of this model in a multi-domain and multi-physics simulations, and to finally support the full model life cycle of these models. So, in fact, the solution has been, we imagine as a solution to set up a real gateway between the conception of the model in the R&D world and the final use of this model in the industrial situation. So this gateway relies on three basic components. First, standards and methods to be able to pass from exploratory works to standardized and certified components that can be used by the whole scientific community, but also by the industrial actors. Around these standards and methods, we build a model repository, a central model repository, where every model will be committed and will be achieved for every users. We also developed a simulation platform when all these models can be used together by every research engineer, and all this is supported by a lot of tools that has been put at the disposition of all the users. The expected result was to support all the model life cycle from the initial conception to the final use in industrial situation, and considering that this model will have to jump from step to step, being in the first conception, initial conception, the model is full mathematical scientific expression of the problem. Then they will have to be refined, to be fitting, and to be adapted to the industrial situation, and then finally perhaps to be optimized or even be used to produce a surrogate model for the use in real-time industrial situation. Thus, based on this consideration, we started to build some 6 or 7 years ago now what we call the Diabolo solution. So the Diabolo solution is first relies on a centralized model repository and a depot. It says that, in fact, in a centralized repository, every research engineer will publish, in fact, its model as an executable component, be it developed in C, Fortran, Java, Scilab, or Python, or even as Excel sheet, for which we will make tailored custom wrappers, in fact. And so it publishes its executable component, but also the scientific documentation that accompany, that make his work usable by other colleagues in the research community. Then he will follow a model publication workflow and describe every part of the technical specification of its model. In fact, it will describe the interface complying with the standards we set up for the platform, and it will also enter all information so we need it for the end user to use correctly this model, to understand how to use it and how to feed it with its own data. Then the system will be able to use all this information described by the user to generate all the gateway needed to have, in fact, this model available as an Xcos module that will be then so compiled, packaged, and published in a depot. So every user will be able then to synchronize its local platform with the model that has been published in this centralized depot, and then use potentially every model that has been developed and published by any other research engineer in the community worldwide. So when, of course, you understand that this global platform is based on Scilab, of course, even if I not precisely mention it. So we develop, we set up, in fact, an Atoms depot in the ArcelorMittal intranet. And this depot is completely dedicated to, in fact, research model developed by ArcelorMittal research engineer. They will also find some specific tools that have been designed and really imagined for the day-to-day use of the research engineer, for their analysis, for their study of sensibility, and in fact for all the technical assistance they have to do for the factories, which are in fact the customer of the work of research engineer in ArcelorMittal. Then they will be able to retrieve and install any of these tools and any of the published model. The model will come as a full operational Xcos toolbox, along with the help, using the help system, and so the user will be able to directly access information needed to use correctly this model in the whole system. Diavolo is also a powerful and user-friendly toolbox set. He said that, in fact, the model will come with a sophisticated inner diagram. In fact, it's not only the model itself, but we developed a global multiplexer that make possible to reconfigure fully, in fact, all the entry data port of the model. It says when the model is at the initial conception, the researcher have to use all the process data needed to modelize the phenomenon and to calculate the solution. But when you are making a dedicated study, sensibility of a particular use of the model, we don't use to feed all this data of this model, or you even want to feed them in a different way, in different orders that they were conceived in the initial conception. So this system will, with this system, the researcher will be able to completely reconfigure all the data entry and for input and output data with a graphical interface, creating new data ports, distributing data in any of these ports, and hiding or showing any of the part of the data for the model. Some advanced block also comes with user-friendly interface. It says we have packaged, in fact, the optimizers and other analysis tools, and they comes with a Java user-friendly interface, so that any end user can use this sophisticated tool for his day-to-day use. And we also develop some specific blogs that permit to develop direct specific simulation blocks by trying some programming or making some specific analysis, or for example, inversing a model by using some traditional techniques to make the inversion of a model and so on. Thus, all this tool, with all this tool now, all peoples concerned with the development and the use of numerical scientific model in ArcelorMittal R&D can use in a very simple graphical way all models that have been published by their colleagues. They can chain these models, making complex simulation schema involving every model, but also all the tools that have been put at their disposition for data access, for parametric studies, and also very powerful blocks for making optimization or reverse analysis of their models. We also have developed a lot of sync blocks in order to visualize all the results. They are really dedicated to the day-to-day analysis. For example, sensibility analysis is something that is very, very often used. So we have developed some tools really dedicated for this kind of analysis and packaged for this. So making very easy, in fact, the day-to-day use of the platform. Thus, what is Diabolo today? Well, global R&D in ArcelorMittal is distributed worldwide. So you can see that we have quite a laboratory in each continent. It's a population of 1,400 peoples. Among them, in fact, more or less 300 people are concerned by the development and the use, day-to-day use of numerical models. So Diabolo today is really used by, something like, 7 laboratories worldwide, and each one giving its contribution, in fact, in development and publication of their model. Some ones are very dedicated to automotive model development, other ones are dedicated to product model development, and some to process modelization and simulation. So the ability to connect in the same simulation environment, process simulators and product model development make really a great opportunity to in fact, to develop some very useful process and develop also some advanced scientific study. Let's focus now in the second part of my presentation on some very interesting advanced use cases that have been achieved with the Diabolo platform. So the first one is what we call the building physics simulator concept. In fact, the idea was here to set up a multi-domain simulation in order to tackle with the physical properties of a building in order to optimize, in fact, its performance in terms of life cycle assessment, energy consumption, and sorry, Microsoft is making me some, okay. And by using, in fact, all the models already existing of different parts of a building that have been previously developed by R&D, and putting them all together to make a sort of global design of a building, and then optimize all the global design using a multi-objective optimization block that have been developed previously for advanced design system studies and optimization in automotive field. So this block, what we have called Optim Advanced Design System Toolbox, has been previously developed, an exploratory project. It's a conjoint work between ArcelorMittal R&D and INRIA. It's a multi-objective optimization module based on surrogate model construction. It will use a non-dominated sorting genetic algorithm to optimize this surrogate model, and then non-dominated solutions are extracted using a Pareto filter. It relies on 3 additional Scilab toolbox, DACE, that is the Kriging model implementation in Scilab for the generation of the surrogate model. We use SVM-KM to reduce the number of variables of this surrogate model, to order and reduce the number of variables. And then the NSGI2 algorithm is used to fitting this surrogate model. Then the block will enter in a cycle, iterating and building, refining at each iteration the surrogate model, and then optimizing the global design system that has been set up under the optimizer. So a GUI has been developed to set up this block that is really complicated, even if all the processes are making it very automatic. In fact, the user here has only to define the variables of his optimization, the objective of his optimization, and the boundaries of each variable as it is. He will be able to program a projection, a discrete projection of his design of experimentation. It says sometimes, of course, the space of solution could be discrete, but the optimizer will obtain some continuous solution. So we will have to make projection on your discrete space of solution, and it will also be able to program constraints on the solution in the form of, in fact, logical relation between the different objectives. Then the purpose was so to use already existing modules to simulate some particular aspect of the behavior of a building. The first one was what we call ACE, which is a freeware, a free available module that has been developed by ArcelorMittal Building R&D. This software deals with, in fact, the footprint structure of the building, and we'll be able, from a footprint, to design for a footprint and the span of in each direction, to, in fact, calculate the total weight of the structure, selecting the good beam corresponding to all the charge of the global bâtiment, and also calculating the total weight and the total price of the structure. We also used some models, as you can see, developed and implemented in Excel, to calculate the mechanic and the thermal properties of the facade, while the global project definition was just entered by the user. He has to give some information about the building use, will it be industrial or habitation use, its time life, its localization, the type of facade, the percentage of opening on the facades, and the kind of heating and cooling system used in the building. Then, in fact, the optimization module will be simply used to generate the optimization variable will be the grid span in both directions and the thickness of the facade component. Two other aspects of the building that has been simulated was the energy consumption. So the global structure and also the thermal properties of the facade can be used by a software, a commercial software that is called Transys, that is really dedicated to the simulation of thermal performance of building. Has been used, so has been monitored from Scilab to calculate the energy consumption for heating and cooling. And then another module developed in Excel by R&D was able to calculate the quantity of CO2 and the primary energy demand for this same building. So the whole data computed by the different module has been used to set up the objective of the optimization module. It's a CO2 emission, total cost of the building, and energy for total heating and cooling. The result, the global pillow schema has been completely set up and calculated in Diabolo. The optimization process is fully automatic, and it's fortunate because, in fact, a full simulation lasts about 20 hours. So we start up the process and then just coming back at after some hours to see the global result. The design of experimentation is completely saved at each iteration, and we are able to restart, in fact, the simulation at any step. So, in fact, you can add hours and hours of simulation, refining your result. And then, in fact, we have found that some very original combination of span and thickness of the facade that absolutely not correspond to the traditional way of designing a building, showing very best performance, a better performance than the one that can be constructed. So it's very promising, and all this work is currently used in the setup and the programming of professional modules that I cannot speak about today because it's still confidential. So I will just let you imagine how we can use this kind of result to really set up a professional module, end-user module to, in fact, optimize and calculate the global performance of a building. Steel frame building, of course. Okay, let's focus on a second advanced use case of the Diabolo platform. In fact, one of the purpose in the life cycle, one important step in the life cycle of a model, when they start to be used by, in fact, the real customer of R&D, it's people in factories for day-to-day expert analysis or even for the use in the production process. In this case, in fact, the purpose was to release and, of course, quickly release some models for process to be used by the expert in the factories. So, in fact, once we have the model completely packaged as Xcode toolbox, they also come as gateway for Scilab. So we are able, in fact, to distribute them as a module. And so we set up a global architecture using the module issuing from Diabolo as, using the Scilab engine, computation engine, to run these models and a graphic interface to monitor, in fact, the execution of the model according to the data that have been entered in fact, a very rich graphic user interface. So, Scilab engine has the model for model running. The models are directly distributed as Diabolo modules, so it's very easy and quick to retrieve a module and to plug it behind the facade of the application. We develop a generic Qt widget to capitalize, in fact, in the development of graphic component because they are coming back, even a lot of models use, in fact, the same concept. So this widget can be reused a lot of time. And some models, in fact, and some combination of models, because behind this facade, we have sometimes 3 or 4 models that are chained, in fact, as Diabolo modules. And finally, they represent the full simulator of a process tool, like, for example, hot strip mill. And in this case, the graphical user interface has been really sophisticated and dedicated. You can see really graphic manipulation of the configuration of the different cage, of the different steel cage. Okay. This way to set up and to package the model has significantly speed up the model delivery process. In fact, we have now 20 single or chain models deployed in factory in this way, and more than 200 users using the model issued from Diabolo, but behind this kind of graphical interface. Let's focus now to end this presentation of the third use case, the statistical model toolbox. In fact, we develop, in this case, we will see that, in fact, the cycle is complete because, in fact, the models are conceived, refined in R&D, and then deployed in an industrial platform to use in online qualification of products. So it relies mainly of a Diabolo toolbox that have been ported from S+. In fact, S+ is a commercial implementation of the R language, so statistical language. So for numerous years, in fact, a service in R&D, which is called Quality Product, dedicated to the study of quality product, has developed this statistical toolbox in S+, that is able, based on the Vapnik model, is able to automatically generate linear regression from process data by selecting the most influent data and performing, in fact, the most efficient linear regression considering a set of process data. The generation is completely automated, and the toolbox allows also the optimization of the model, and it comes with a lot of analysis and filtering tools that help to correct the process data, to refine the model generation, and so on. It relies on three additional toolbox: the ScilabTec to calculate the linear regression, the NAND toolbox for clustering and correlation, and XLSLink to make some report and data import. In fact, the whole generation of the model is based on the use of the Vapnik model, which will be able to sort data according to their influence of the variance. In fact, it's ANOVA analysis, and thus it will select automatically the data that have to be retained for the better representation of this set of process data. Thus, in fact, the whole toolbox have also been deployed as a graphical application, Windows application. Thus, in fact, the process engineer in the factory have its own installation of the tool, is able, from its process data, to set up the first version of his linear or pseudo-linear model. Once the result is okay, correct for him, he can export the whole project to its colleague in the R&D lab, which will be able to retrieve the project, to refine the model, be it in the application or in Diabolo, because everything are completely compatible and can work in each environment. Thus, he can also optimize or really refine this model. Then he will be able to deliver this model in a configuration management system. This configuration management system will be then used to update the platform that are deployed in the factories to day-to-day quality control process and automatic product qualification for the production in online. Of course, these models are statistical models, so they are constantly observed in statistical process control, and once the user can state a derivation from the result, because in fact this model calculates mechanical characteristics, and sometimes some trials are made of the products, so we can compare the result of the model with the trials. And once we observe a derivation, we enter again in the full cycle, resetting a new regression and then validation by the researcher and publication in the configuration system management. Okay, so this was the last slide of my presentation, and I want just to say how we are very interested, of course, of further development in Scilab. I saw some conjunction in the axis. Model reduction is for us really not for this time optimization, but really to have surrogate model to be used online in real time in the factories should be really an advantage. We are focusing, we have some exploratory project in this domain. We are also very interested in standalone application generation, because as you see, we have in fact two populations that may exchange the resist engineer and the quality process in factories, and they need to have this kind of possibility to set up full graphic application to be used by end users in factories. And of course, optimization tools and optimization performance are also a great concern for us, because we are deeply using this kind of module. Scilab V6 is the current subject. We have ported all the statistical toolbox has already been ported to Scilab V6, and Diabolo, it will be the task for the next year to port it to Scilab V6. Okay, thank you. If you have some more questions.
Thank you, Stéphane. It's a wonderful presentation. I discovered
it's a lot of years of work. It's not.
Yeah. I saw some of it in the previous presentation from, I think, 2011, 2013.
Yes. All right. So the full story of Diabolo, the Diabolo framework, has been presented for the first time. We were just setting up the first version of the toolbox in 2011.
Now I see some of the PIDO. I think this is new, the process integration design optimization, right?
What is interesting is that the community, the resist engineer community, has really taken the tool and is using it day to day now. So you can say that we have 100 users of Scilab, indirect user of Scilab in global R&D in ArcelorMittal.
Well, that's great. Do you have maybe from the audience some questions around statistics, optimization? We have an expert here, so if you have questions about that. Well, anyway, we have a Q&A also later at the end of the day, so if we want to discuss about, you mentioned model reduction, some application development and so on, so yeah, we can address that in the end.
Okay.
Thank you, Stefan. So we have one last presentation, and afterwards we will have a session meet the expert at our break. So if you want to register to ask some questions about model reduction, here we have an expert on optimization and such simulation subject. Hugues, also related to XCOS, there's Clément who's here. So if some of you are using some of the system, dynamic system modeling, and Antoine also is here for everything that goes around Scilab, the architecture, even Scilab Cloud. So you can register. I think it's just outside. So here, it's on the entrance. You can register. So the next presentation is from my beloved friend Jean-Pierre Beauvais. So let me shortly introduce you properly. Well, I should know all of this, but I'm going to read it anyway. Jean-Pierre is an engineer from a very famous French university, Arts et Métiers. He has a PhD and is currently working on energy projects, helping companies cut their energy bills. After 30 years with the pharmaceutical industry, R&D, production, corporate, in the last 15 years, he has been working on process control and HVAC. Yeah, it looks like it's a current concern for us, HVAC. Sorry for the cold. But at the time where a critical global warming is looming on the horizon, with a 3-degree increase expected by the end of this century, it is paramount to look for any means to curb this devastating trend. Yet not demonstrated that humanity will survive this episode. It's quite dark what you're writing. Huh? So we can state that many companies' life are already at stake, sometimes even not being aware of this imminent threat. While optimizing energy production is one of the most common responses, cutting energy demand is far less addressed, yet presenting a largest potential in terms of potential savings. Energy Cut delivers consulting and advice on the best way to cut energy demand fast with demonstrated payback for both the enterprise and the planet. It looks like a good agenda for today. So that's it. Tu veux aussi la page web? Ah d'accord. Tu veux aller sur Scilab Cloud? Je vais directement.
Tu es admin?
Si groupe.
Tu dois être admin?
Oui, c'est pas ce compte-ci.
Si tu avais laissé un truc derrière.
Opti-clim. Voilà. On va le laisser charger. Tu veux commencer par la présentation?
Non,
je
vais commencer
par la démo?
Non, je vais commencer par la présentation. Pardon, je vais commencer par la présentation.
Alors, attends. Pendant ce temps-là,
Thank you, Jan, for your kind introduction. So, let's talk about energy, something very necessary today. Okay. Let's have a look to energy over the pharma industry first. Okay. Well, so these are figures from Sanofi, my former company. Manufacturing amounts to 30% on average of the total energy that is consumed in the company. And climatization, HVAC, standing for heating, ventilation, and air climatization amounts to 60%. Lighting for 10%, say nothing. So, gas amounts for 53%, electricity 47%, say 50-50. And now, if we look at other competitors in the pharma industry, we see that the main clients are respectively production, R&D, surprisingly, and packaging, bottling packaging. In pharma industry, we have actually two big areas: chemistry, that manufactures the API, active pharmaceutical ingredient, and the second part of the industry is packaging, tableting, filling, packaging, all these activities. Wow. So overall, 50% goes to electricity, 50% goes to gas. Motors amount to 70 to 80% of the total electrical consumption. And HVAC amounts to 60 to 70% of the total consumption. So it's a major part of the energy that is consumed by this industry. This is valid as well for other activities like cosmetics. And the food industry is not too far from these figures. Let's have a bit look into the technologies. So heating is done using heating coils, a kind of exchanger, cooling coils, hydraulic distribution to convey the fluid to the coils. This is done through networks, valves, pumps, all that. Fans, okay, to supply the air into the rooms, and fans to extract the air from the rooms. Fans that are geared by motors, electrical motors, with bad or good efficiency. Control systems that are really paramount in this area, and that can bring very terrible performances sometimes. And air filtration, especially in pharmaceutical area and in electronics, by example. The quality of the air is paramount. You know, when you are manufacturing injectable products, you can imagine that we do not want to have any particles. So the number of particles in the air is severely controlled. And due to that, the air is filtered accordingly. And, of course, to be sure that we have exactly what we want in terms of regulated parameters, We have to take into account temperature, that is somehow critical for some process, the humidity, critical as well, the air change rate, and the pressure that guarantees the avoidance of particles. And we have to take into account the pace of the work in the plant. Okay, what is exactly HVAC? Okay, as per regulation, okay, it's a need to supply the air meeting some specific requirement on temperature. By example, for tableting, everybody knows what are tablets. On average, the temperature should be below 27 Celsius grade. Relative humidity, under 60% on average. For effervescent forms, it's under 30%. The air change rate in offices, by example, as per regulation, we must have 2 volumes per hour and per human. And the air purity, and this boils down to particles again. Okay. This is a typical air handling unit, with fresh air incoming here, with a damper here that can be controlled. Red means controlled, you see. So the air is incoming through filters, then going through a heating coil, which is controlled by a valve. Then it is it goes through a fan, the supplying fan, a cooling coil, another heating coil, and sometimes a humidification, which is again necessary, and then incoming into the room. So the room is has various characteristics like its size, the tightness, the insulation, and a number of controls are performed, such as temperature control, relative humidity control, pressure control, and air change rate control. So it's a pretty complex system, you know. Well, the air is extracted by a fan, and a part of this air is recycled here through a damper that can be controlled as well. And more or less big part of the air is extracted through another damper here. Okay, so we were facing in the company, we were facing this challenge. We were facing a big source of energy consumption with the awareness that a big savings were possible, but not knowing how to start and what were the most critical parameters to address first. We had a look to the market, and we were unable to identify an easy model, easy tool to put that in any user's hand, to be able to quickly figure out how to start, which parameters were the most critical. Because the factors are very diverse, they powerfully interact. There, of course, on top of that, linearities are numerous. We have in this model more than 40 equations. And, as I said already, no tool was available. So that energy managers were saying, okay, you ask me to do something, but actually, I don't know if I have to improve the fans, if I have to look at the fluid distribution network, if I have to speak with quality regarding the parameters. So we realized that a tool was necessary. And it was the beginning of this decade. And this is the way we address that. At the beginning of this decade, we first decided to build a draft. In my mind, it was clear that it was only a draft because it was done with Excel. I will come back on this point further. And it was pretty complex to build this tool. And some simplifications were necessary because of the limits of Excel already. However, we were able to qualify the tool and to validate it with some real examples, so that, in spite of my reluctancy, this model was deployed based on Excel, was deployed by something like 2013. It was deployed on a very reduced number of sites, and we were lucky because it was really a mess to be able to manage the deployment of such Excel-based model. The size of the program and the data was already beyond 200 megabytes. So you see, we were having some problems with our infrastructure in some countries at that time. So next year, we decided to rebuild the application, and this time based on Scilab. Scilab was the main contributor for the project, except for the algorithm for the calculation itself, but it's a small part of the program itself, something like maybe 10%, no more. And we first deployed a local solution based on a very usual deployment, but it was not very easy to manage due to the updates. Numerous updates were necessary. So that 1 year later, we decided to transfer the application that was running pretty well to the cloud. And I think this application was the very first application for Scilab to going to the cloud. It was done very quickly by the same dream team, and the application is hosted today by ESI, and or by Google, but via ESI. And the deployment started in 2016, very quickly. So that today we have 52 sites regularly connected and 92 users, registered users, who day to day are using this tool. We are going to see how it works to cut their energy bill actually. The decision was made this year to extend the usage of OptiClean to other companies. So, so this is bill, well, the energy bill that is cut. Okay. All sites were able to cut their energy bill by 2-digit savings. So it's already a big success, and sometimes reaching 50% of savings, and even more in some special case. And nobody was able to believe that before starting. And not only this company, but all of those companies have this huge potential with HVAC. So, how they did that? They first started to question the parameters, okay? The dead band on temperature, on relative humidity, because the very facile excuse was, I'm not guilty for that. Quality asked for that. Okay, just please call quality. And quality was saying, I never asked something so accurate, you know. I just want the temperature being below 27 Celsius grade. But what was really implemented at the plant was 22 Celsius grade plus minus 0.5 Celsius grade. This is just terrible in terms of savings. Okay, the smallest, the dead band, the largest, the expense in energy. The air change rate was questioned as well, because in some plants for manufacturing the same product, in 2 different plants, some were using 60 volumes per hour, while others were using 30. So why having this discrepancy? 60 is a huge waste of energy. And the implementation of eco mode at night, out of working hours at the weekend, was as well something very important and considered. So this was done without any investment, meaning that they were able to cut their energy bill by sometimes 20% and sometimes more, not investing anything, just discussing with the quality department. In the second time, they decided to modify the technology, so improving the temperature control, temperature and humidity control. We should teach people here how to do. And improving the fluid network efficiency as well. Increasing the motor efficiency, the gearing, all that. And sometimes as a secondary effect, very positive secondary effect, they avoided to invest in unnecessary chillers, transformers, boilers, and so on. Okay. Okay, here investment was necessary. So now, quick demo. Where is it? Could you help me?
Yeah, it's here.
Okay. Thank you. So here you can see the data. We have data on the room itself. It's in French. Sorry. On energy and control, air handling unit with volumes per hour. Okay, so I prepared a demo. And we have energy recovery as well. It's a bit okay. The cloud is far. Optically means the cloud with diamonds, you know? Optically means... No? So, okay. So let's see at the room. The set point on temperature, humidity, the size of the room, insulation of the room, all that. And since time is running, let's calculate demo effect. No. So, more than 8,000 times, the algorithm is executed hour by hour over 1 year to be able to calculate what is the consumption of energy. And the consumption of energy is represented by the cumulated energy over the year with heating, with cooling, and with black ventilation. Here are the results as figures. Okay, this is consumption of gas, electricity. You see the figures are already significant. And let's now try to modify something. We copy the values in the simulated situation. So we started from 22 plus minus 1, and we were going to change that to 2. Just that as a change. Just changing 1 Celsius grade as a dead band. And we can see what we can expect as savings. And you see, it's really significant. Just 1 Celsius grade means we're saving 10% on heating, 21% on cooling, nothing on ventilation as expected, and overall it's around 10%. Just 1. Almost done. And let's just change now. Let's cut the ventilation, which is absolutely huge. You know, it's absolutely just terrible. Aha. It's right. I have to change. Okay, so you see it's very significant, so 67%. So that's the reason why I told you that people are not so much aggressive towards energy. In many plants, it's just business as usual. It's running. It's part of the running cost. And as soon as you start to question that, of course, it's a different story. I would like to come back to the. Okay. To come here. Okay. So. So, to summarize, so the energy costs are expected to increase in the coming years. You understood that. Carbon tax will follow. Many HVAC equipment have a two-digit potential savings. And doing this work usually even increases the quality standard, so double winning. So does optically have a brilliant future? You know, global warming is not a legend. We can experience that, apart from today. So as it is speeding up, we need more and more climatization. And since climatization is very poorly installed and set up, it increases again the warming up. So it's a vicious circle that a tool like OptiClim can really help breaking. Thank you.
Thank you, Jean-Pierre. Some of you have questions, maybe? We can also take it to the break and have some coffee to warm you up. And we'll be back in half an hour. If you want to meet the experts during the break, well, you can subscribe over here. And Clément is already smiling, so I think he wants to meet you. Ça va? Went good? Le père Muller, tu me...
No, no, for French you have to go to
D'emploi, alors, on n'a plus de vidéo. Je crois que la vidéo est partie. Est-ce que la vidéo va revenir? Sur les touches, c'est gauche, droite, au bas. C'est le système international. Là, tu es en repère galiléen, donc tu peux continuer comme ça. Là. Si tu veux faire des changements de repère, tu as ScilabTec pour ça, c'est assez performant.
Oui. Ah bon?
Oui, pareil.
Moi, ma présentation n'est pas hyper longue, je crois que je...
Non, bah là, c'est à la fin, là.
Attends, alors du coup, j'ai rien compris.
Ben, ça, c'est gauche, et ça, c'est droite. Et...
Ah d'accord, d'accord.
Et puis bas, ça fonctionne aussi.
Il n'y a pas de pointeur, hein.
Non, désolé, j'ai pas de pointeur.
Je n'avais pas prévu.
Est-ce qu'on a quelqu'un qui peut nous recommencer la vidéo? Sinon, on va... Et c'est parce qu'il n'y a personne qui est... Je sais pas. So for this next presentation, I'd like to welcome on stage Alain Lamy from the French Space Agency CNES. His current job is space mechanics senior expert. He's graduated from ENSET Engineering School in mathematics and computer science in '87, joined the CNES in '89 as a space flight dynamics engineer. He's now a senior expert in space flight dynamics. His main activity is on mission analysis for various projects in early phases at CNES. Previous experience includes development and operation of an autonomous orbit control experiment on the CNES microsatellite Demeter. In-flight implementation took place successfully for 4 years, from 2005 to 2009. He has also been involved in the SWOT, joined CNES GPL. What is JPL?
Jet Propulsion Laboratory.
Okay.
NASA.
It's NASA. Altimetry mission and responsible for the mission analysis at CNES. Member of the CCSDS, okay, Navigation Working Group, standardization of data exchanges related to space flight dynamics. Member of the International Symposium on Space Flight Dynamics, and provides trainings on astrodynamics in various engineering schools, ISAE, SuperHero, and NAC in particular. Alain.
So thank you, Jan, for this introduction. So I work at CNES, French Space Agency in Toulouse, on mission analysis. So mission analysis means, in particular, determining the orbit that is best adapted to some missions, and also to analyze various aspects related to the trajectory of some space object, with the orbit, and during the mission, at the beginning, end of life analysis, and so on. And my talk today is about orbit propagation. So orbit propagation means how to determine the orbit. The orbit means the position and velocity of an object in space at a future time, knowing some initial conditions, so the position and velocity at some initial time, and I will show an application to the Mars Phobos system. And I also wanted to say that this presentation is in line with activities taking place now at CNES. In particular, there is a mission in cooperation with a Japanese space agency called JAXA, a mission called MMX to Phobos, in which CNES is involved. And some of the examples that I will show are, in fact, results from this studies about this mission to Phobos. So a bit of context and background. So at CNES, we have started using Scilab about 10 years ago for mission analysis, that is to say, spaceflight dynamics mission analysis. As I said before, the study of orbits and all aspects related to the orbits. One particular contribution is ScilabTec. It's a toolbox available on the Atoms website. So the first version was created at the end of 2009, so almost 10 years ago. And it was updated recently, very recently, last month, and now is compatible with Scilab 6. So in ScilabTec you have various functions, about 250 available functions that are part of the user interface related to various aspects, analysis about orbits that have some properties, reference frames, timescales, and orbit propagation with some simple analytical models and things like that. So in fact, you have two parts. The original toolbox, which is called ScilabTec, is in pure Scilab code, so only Scilab, nothing else. And there is an extension that has been created, I don't know, maybe 5 years ago. And started, in fact, with Scilab under a contract with Scilab Enterprises for the first version. And this second toolbox is called ScilabTec X. X means extension. And in fact, there is no user interface available. It's only internal functions called by ScilabTec. And it contains mainly C and Java interfaces to various features that are available in ScilabTec. And at CNES, we also have other libraries and tools interfacing with Fortran, C, and Java for everyday analysis and everyday work. In particular, we exchange data, orbits in particular, with other entities, because we deal with orbital aspects, but there are other aspects, of course, for space mission related to thermal aspects, I don't know, power, and so on. So the other entities and fields use our data and results for their own computations. So this is just a few examples about what we have in ScilabTec. On the left side, you see graphs created with a demo tool that is available in ScilabTec. And you have in particular, at the middle, you have something that is done using a tool called Stella. Stella is a tool available at CNES for end-of-life analysis of space objects. You want to know, in particular, how long an object will stay in orbit, how many years in particular, because you don't want the number, maybe you know the number of debris to accumulate in space, so you would like the object to re-enter at the end of its lifetime. You have over various, about 100 demos showing various aspects, and you have also lots of demonstrations, examples. We have something called Cookbook that gives detailed examples where you can copy and paste and change and modify and run very easily. So as I showed in ScilabTec, you have not only pure Scilab, but also C and Java. So just to summarize the reasons why we want sometimes to interface with other languages. So the main primary aspects for most users is that you want efficient code, and for some applications, Scilab is not efficient enough. So you have to, for very specific aspects that are very time-consuming, you want to have maybe native C code or something like that you want to code from Scilab, but to have a reasonable enough execution time. Another reason, mostly the reason that made us choose to interface, in particular Stellar and other features, is to make existing software available. And the examples in ScilabTec are Stellar, which, as I said, is for long-term orbit propagation. Long-term means many years or tens of years. And another tool that is interfaced is related, I don't know if you know, with TLEs that gives orbital data and model to propagate various objects in space. And one aspect is that the data that are needed as input are available on the internet, so it's very simple to use. If you know nothing about an object, you can get some data and propagate and see what the trajectory is. Another feature is that if you interface, you use the original code, so you have probably, so you are compatible with initial code. There are fewer bugs, less testing effort is required, but of course you have to code the interface, so it has to be worth it, because it's a little bit of work and testing yet, because you have to be sure that the code you develop is compatible, is exactly the same as the original one. And of course, if you publish your toolbox, you are interested in having new users, and they may be interacted with these new features made available. So because it's a conference about Scilab, this is Scilab code. So this is just a simple example that is taken from ScilabTec that can be used to propagate an orbit, so to compute the trajectory at future times. So here at the beginning, you see that you have an initial state, a date. You see the calendar date, which is, I think, no, it's not today, but it's not far. You have the initial state vector, which is given as mean orbital elements. It's a way to describe the position and velocity in a more easy-to-use way. So when you have an orbit, you need reference frames. You need to care about timescales that are usually the most complicated aspects that are more or less hidden in these examples. So you have the final dates. You have structure params that describes the structure of a model you want to use. So that is to say, the force you want to take into account, some various parameters that describe the model, the forces, and then you propagate using the function that is called here Stellar extract, and you obtain the results. So again, mean orbital elements that you can plot, and you have a fantastic plot on the right. So it's very easy to use, and it looks like pure Scilab code, despite the fact that behind all these functions, at least behind the one that is shown in blue, there is a Java code, but it is completely hidden behind the interface. So about numerical integration, so it's something that probably everybody here knows. And for us, for our applications, the objective is to compute the position function of time as a function of the initial state vector, position and velocity, and also as a function of model parameters, that is to say, the force. So you have the acceleration, that is to say, the force divided by the mass. You integrate twice, and you obtain the position. So that's not very difficult in theory. So you can do it easily in Scilab. You have examples in ScilabTec using ODE that can be used to integrate the trajectory. And on the right, you have an example, so it's not very complicated. You have a force described by the function you want to integrate, the initial state vector, the final date, here are seconds, and you obtain the trajectory as the result of the call after calling the ODE functions. So a few lines is enough. It seems okay, but the problem is that the computation of some forces can be very time-consuming. That's the case, for instance, for the force that describes the effect of the Earth, because the Earth is not a single dot with a mass. It has a complicated shape. It is represented by a function that is called potential, that can be developed with spherical harmonics to high degrees and orders, maybe 100 for the most precise one, or even more. And so it takes time to compute this kind of force. Another force that takes time to compute is the drag, the effect of drag, the atmosphere on the spacecraft. And so for this reason, it can be possible to do computation for a short period of time, but for a long period of time, it may be hard to have results in a reasonable enough time. So one possibility would be to rewrite things in another language, but it would be, of course, a lot of time lost because it needs testing and so on. So that's not the reason, the possibility we want to use. So what we have decided to do is to interface Java. And why Java in particular? It's because a library at CNES exists for library for flight dynamics studies of software exists. It is used in future. It will be used in future control centers. So for operations of satellites will be launched in the future. It's called Patrius, and it's also freeware. So if you're interested, you can download it on the website that is shown. It contains lots of aspects that can be used for computation of trajectories, the forces I was talking about just before. And so the idea was to design an interface a bit similar to what we did with Stellar for numerical integration of motion. So that's what we did. And as you see, the example is quite similar to what I showed before for Stellar that we have in ScilabX. This function is not available in ScilabLab, it's available in internal tools now. Maybe in ScilabLab one day, but not now. And so you see that it's very similar. You have an initial state, you have a model that is described in a structure that is converted in the Java interface into an object, Java objects. You call the propagation function and you obtain the result here, position and velocity, that you can convert to orbital elements. That is more easy to analyze. And here you have a plot of some image axis, that is to say the size of the orbit. So it's quite similar to what I showed before. It's like pure Scilab code, easy to use, so it's perfect for our studies. And some of the features, so you have a simple interface as I showed. It computes the position, velocity, acceleration from initial state vector, but not only, you can also compute the derivatives at some of the position velocity with respect to the initial position velocity, also the derivatives with respect to some parameters like drag coefficient or things like that. And so it can be used in more complex applications than just extrapolation, pure extrapolation. You can use it in applications like orbit determination. Orbit determination is very important in practical applications. So for instance, you have measurements from ground stations and you want to determine the orbit that best suit the measurements. or you can use it in orbit fitting. You have some arbitrary trajectory and you want to know the initial state vector, so that if you propagate that state vector, you are very close to your arbitrary trajectory. And so just one remark about the design aspect. So you have code that does the interface in Java, and we have decided to have the Scilab code part of the interface as small as possible. And so as much as possible is done in specific Java code. So initially this function, this tool, was adapted to Earth applications only. So only orbit could propagate only orbit about Earth. And so we, because we wanted to apply it to our Mars Phobos mission, we extended the code to deal with other bodies, celestial bodies than the Earth. So we introduced elements to describe Phobos and Mars bodies. So you have some characteristics of Mars and Phobos. So Mars, the planet you know, at a distance 1.5 distance of the Earth to the Sun, so not very far to the Sun. Radius slightly less, or maybe twice as less than the Earth. And Phobos is one of the two Martian satellites. The other one is called Deimos, and as you see, it's very small, about 20 kilometers in diameter, and also very close to Mars, less than 3 Mars radii, compared maybe to the Moon. If you compare to the distance between the Moon and Earth, which is about 50 times the Earth radius. So Phobos is close to the Mars, and it's very small. So if you're far from Phobos, the effect of the gravitational effect of Phobos is very small as well. But in this case, for this mission, MMX, as I mentioned before, we want to observe Phobos, so have a trajectory very close to Phobos. And in this case, Phobos, the effect of Phobos becomes is not negligible. And so the orbits we study for this mission are called QSO, quasi-satellite orbits. So it's really orbits about Mars. So the object is orbiting Mars because Mars has a bigger mass. But you want to be close to Phobos to observe Phobos from close enough. And so the orbits that are chosen are shown here. So you have, you see Mars at the bottom and the orbit of Mars, and the orbit of the objects has a period identical or close to the period of Mars. And so if it is the case that you see at this position, the object is close to Phobos. And half an orbit later, the object would be here, and Mars here. So it's as if the object was orbiting Phobos. In fact, it's orbiting Mars, and Phobos is only a perturbing effect, if you want. But if you're close to Phobos, the perturbing effect is not negligible and has to be, of course, taken into account. And even taking into account the actual shape of Phobos, as you see, the shape is very irregular, so you need an accurate enough model to take that into account. So these are typical studies that have been conducted in the framework of a project. So typically, the first part of the study consists in having a simplified enough model, analytical model, where you can design the orbits that are well adapted to the mission. So you see example here. You have orbit with some property, and in particular they repeat after some number of orbital periods. And typically what we want to do is to check that the orbit we have designed with simplified models are close enough to real orbit that you propagate with more accurate model. So you can do with using the tools that I showed, you can adjust the initial state so that you can fit the orbit with the accurate model to the less accurate trajectory computed with the analytical model. You can, what we did also is something called multiple shooting, that you adjust the trajectory on consecutive arcs and things like that. We have also an internship at NES that studied orbits close to the Lagrange point, but that is very close to Phobos. If you don't know what it is, it doesn't matter for this presentation. And so here are examples of orbit propagation that we did using our Java Scilab interface. So I started here from an initial condition that we used for testing, because we test the software, we compared the results with another software just to check that the results were correct. And so you see the trajectory in a Phobos-centered frame on the left. And so you see that the trajectory is quite strange, and that's because the Phobos is not far, so it perturbs the motion in a non-negligible way. And if you because also Phobos is not the center of the motion is Mars, and here Phobos is only a perturbing effect, as I said, so you have this strange trajectory. Of course, if Phobos was the center of the motion, the main center of the motion, the typical trajectory you get for object is an ellipse. You would get an ellipse. Of course, you see that it's not really like an ellipse, because it's not an orbit about Phobos, and Phobos has a strong perturbing effect. And on the right, you have the same trajectory, but in a rotating frame. Rotating frame is a frame that rotates at the same rate as Phobos. And so you have here something that is more closer to ellipses, but are changing with time. And so because of the effect of Phobos, the trajectory are very sensitive to initial conditions. So I did not want to show accurate, a lot of results here, but you see that on the plot that is shown at the bottom of the slide, you see results of lots of propagations, and you see the yellow dots that gives the trajectory for which the spacecraft crash into Phobos after less than 1 week. So you see that there are yellow dots scattered all around the plot. So it means that you have to be careful for a given mission, you have to be careful to check that your trajectory is stable enough and that you can control the trajectory, just to be sure you don't crash into Phobos. So that's the end of my presentation. The main objective of this presentation was the interfacing Java and Scilab, and it showed it's clear that it's rather easy to interface Java and Scilab. And there is no compiled code. Compared to an interface with C language, I think it tends to be easier, because you don't have the complicated API. It's more straightforward to interface Java than maybe C. One possible limitation is that you could have incompatible libraries in the Java class path. That could happen. In fact, it already happened. We observed this kind of thing. If you have different libraries with incompatible versions, it could be a problem, because everything is on the same list of libraries. So that may be problematic in some applications. And for the applications, we have ACNES, Stellar, in ScilabTec, and also what I showed, our new orbit propagation function. We are very satisfied with the results, and the tools that we have been used in studies, in projects under study, like the Mars Phobos application. And so we are continuing this direction, I think, to continue with Scilab and continue with using interface when it is necessary and when we have libraries that we want to use and made available in our set of tools that we use for mission analysis. So that's all for my presentation. I have just one remark that concerns the Java, its Scilab interface. This is just a basic examples where you can, that shows how the interface is used in Scilab. You import the Java class. You can create an instance of this Java class. You do some calculation, so it's not very difficult, as you see. And at the end, you have to remove, using a special function called JRemove, you have to remove the objects that have been created. And this part is quite tedious, because it's like freeing memory in C. You have to be careful that you free the memory you have created using the jimport and jextrapolation functions. And if you forget to call JRemove after some number of calls, you have memory leaks, and Scilab crashes after some time, or not crashes, but freezes or something like that. So you have to be careful. So I suppose that some improvements would be worthwhile, just to improve that aspect and to make it even simpler to use. So thank you for your attention, and if you have questions, I'll try to answer them.
Thank you, Alain. Do you have questions to the French Space Agency? Yes? Okay, we'll proceed with the next presentation. Thank you again, Alain. So the next presentation is from Sophie Missonnier from Bertin Technologies. She's a project manager in simulation, modeling, and optimization. She's an engineer in the domain of modeling and scientific computation since her graduation at Polytech Lyon in 1998. So 20 years of professional activities, starting with development and use of simulation for understanding physics and interaction. The study of state-of-the-art feasibility and innovative system research and development. Then focusing on system design thanks to models and optimization in various domains, space vehicle, Formula One, energy sector, and project management, simulation process rationalization, system design and optimization, data analytics, physical phenomena modeling and simulation, and scientific software development. She has been applying those technologies based on mathematical and computing tools, and now in charge of methods for multidisciplinary optimization, including model order reduction, and running one current running research project called Mordicus, where we are actually collaborating. So, Sophie.
Thank you, Jan. So, I will present modeling work that we made a few years ago for Yamal LNG. So, Yamal LNG is a joint venture integrating Total and other partners, which was set up for utilizing natural gas resources in Sabeta. Sabeta is a field in the north of Russia, which is located above the Arctic Circle. So, you can see on the picture, from Sabeta, the shipment of the LNG will be sent to Asia market mainly, and through the Northern Sea route, which is really shorter than the Southern Sea route in blue, and wait, see that. So for the shipping of this gas to the customer, the sea is very Arctic, near the pole, so the cold conditions are extreme for the ships, and a special ice class ship has been designed and built for this purpose. As you can see, so there are some capacity to navigate without the assistance of icebreakers, but it is limited in the ice that it can go through. To give an idea, so the Yamal LNG project started in 2012, and 1 year later, Bertin has been asked to study some ice-related aspects, and during the development of the project, we did some other work for this project. The first LNG has been shipped 1 year ago, and in 2017, and it's also when we when we had another study conducted for another terminal than Sabeta. So here, yes, sorry, the pictures are a little small. A seaport has been built in Sabeta. So you cannot see it too much, but it's on a on little part of the Gulf. So the weather conditions in this region, as you can see, can be really colder than here today. And this is a good point from the liquefaction process point of view, because it's easier and requires less energy. But for the exploitation, Yamal LNG so has to ensure that the drilling performance goes on whatever the weather conditions are, and also there's to ensure that the ships are able to deliver the production to their customers, so to navigate through the port and the channels to go and to come and to go back to the customers. So there is a problem rising that it is each time that the ice is broken by the vessel going on the channel. So it's broken in small blocks of ice, and due to the cold temperatures, it will freeze again in a very faster piece than if it had not been broken. So with the harbor activity starting in winter, it will induce a lot of ice breakings. And in cold weather, since winter there is about 6 months, from November to April. And this may lead to ice thickness so high that the carriers cannot navigate anymore. So this is why Bertin developed a model to compute this brush ice growth. So the brush ice is a normalized ice block size that is a kind of crushed ice in such conditions of frequent breakings. And its growth is comes from the accumulations in case of this frequent ice breaking in under harsh weather conditions. So this is a thermodynamic model that we developed based on a 1D multi-layer system, as you can see on the figure. It's using the Metocean data for the weather conditions, which are adjusted all along the season. It takes into account the operational events of the ship coming and leaving the seaport, and so we choose to develop that in Scilab. This model is composed of two main components. So the thermodynamic model for the ice growth, which is made by solving the heat equation in a 1D and steady case. with the, as we see in this figure, with the boundary conditions being, so this is the blue central part, with the boundary conditions being the interface between air and ice, and between ice and brush ice. So this is the ice growth model. And there is another part which is the ice breaking model. So the assumption is that the solid ice is instantaneously transformed into brush ice, which is a porosity of and salinity characteristics. And so this model allows to compute the phenomenon during all the winter from November to April, and some conditions lead to ice thickness at some times that is too high for the ships to navigate, and therefore there is a need for the system to reduce this ice thickness. So the idea is to inject warm water from the wharf where the ship comes. So there are the most often navigated zones, and this warm water is diffused thanks to air bubbles injected together. So the sizing of this system takes into account the weather conditions that may be variable from one year to another. But on the average, minus 20 degrees during the 6 months, so colder than in Paris. And also the navigation frequency, which is also variable depending on the phase of activity. And so we did that sizing with the help of the combination of the brush ice growth model that we developed in Scilab and the CFD computations for the ice melting effects. So it's on the left, you can see the brush ice growth model as I described previously. And on the right, we used an hydrodynamics model with our in-house CFD code, which takes into account the tidal currents and the injection of warm water. As you can see on the right figure, the black lines are the different approach channels of the ships. And we also studied the strategy of the ships. The question was, is it better to travel the same channel until it reaches the maximum ice thickness and then to change channels? Or is it better to change channels each time? First passage, first channel, second passage, second channel, etc. And we saw on the left figure that this is related to the first approach that I told, and the vessel goes through the same channel until the maximum thickness is reached. And you can see each green curve, it's the channel, the thickness. Yes, the y-axis is the ice thickness. So we realized a campaign of computations with different winter conditions, and we studied five areas in the port. And we also changed the frequency of vessels passage according to the exploitation phase and also the channel strategy that I talked about. On the upper picture, you can see the evolution during the winter of the ice thickness without heating system. So it's several meters of growth. And on the lower pictures, several configurations of the heating system have been assessed, and we'll see the impact on the ice thickness. Sorry, I had to hide the scales. It's not the same scales, but you understand that the impact of the systems, the heating systems, is shown. So I'll speak about conclusion at the time of our work. So it's a few years ago. In that use, Scilab has been effective for developing such a model based on a 1D partial differential equation, and with input-output by files and plotting, as you've seen. This model has also been reusable some years later and reused for another terminal. But we thought that communication from the Scilab model and the other soft was not so straightforward. I think it's feasible, but we don't always have time to spend for that. So for industrial case, we preferred coupling the in-house CFD code and the MATLAB Scilab model through files in that study. After, we also had difficulties for integrated Scilab models into our iterative workflows when we do design of experiments or optimization or sensitivity analysis. For our case, we use the Mod Frontier optimization environment, and the Scilab node isn't operational, and so it's not usable in a straightforward manner. So our recent developments are somewhat limited on the use of Scilab, limited to the small models or prototyping, which are independent in most often. At this time, still a few years ago, we didn't find Xcos was sufficient also for our specific use. And we also for the modules toolboxes, when we tried it, we often find it was not up to date, or we had some difficulties to use them. And to finish, the Scilab team developed a model reduction toolbox, and using our workbench that we shared with them in a collaborative project. So we plan to assess this one and to see what can be done. That's all for. Thank you.
Thank you, Sophie. Maybe there's here some points interesting for the Q&A later today. On you mentioned difficulties to connect with third-party software. Well, obviously connecting to your internal CFD is something that we cannot do because it's your code. But for integrating with Mod Frontier, maybe you can get in touch with them, because obviously also it's a closed code, so yeah, again, there's nothing we can do. Overall, if there's some requirements that are on the side of Scilab for connecting with third part, it would be very good to try to concentrate them in order for us to have a good overview of what is missing in terms of API, in order to facilitate the interoperability with other software. It's actually one of the, well, spoiler alert, it's one of the things that we want to push in our roadmap, so interoperability is very key. With software, we've seen also earlier today with hardware, so it's a very important point. What would be probably interesting is also to discuss with Clément on Xcos to see what was not sufficient at that time. If it was about simulation only, or if you have further needs on code generation or other capabilities for state machine modeling, I don't know. So this would be very interesting to find out. Those are valuable feedback. Thank you for your presentation. And well, I think we are done for the morning presentations. Do we have questions from the audience? Looks like everyone is hungry. Yes. So, okay. Thank you for this presentation. It gave me some cold just to look at the ice, but I hope this afternoon will be better. So we'll have a 1 hour break, I suppose. 1.5 actually. We are in France, so we'll take 1.5 hour break. And so it'll be also good to exchange with the community. And if you have questions, don't hesitate to, talk to each other, obviously. And we'll be back at 2 for further exciting presentation. Straight coming from the US, we have Botao from Qualcomm. So I think it'll be very interesting. Have a good lunch. Bon appétit.
voir pour le son. Si on peut redémarrer. On peut mettre le live streaming aussi.
So we are soon going to start again for 3 more presentations. We're just waiting for the screens. Will be better. Unless you know all of the charts and you want to describe them to everyone. So we have with us today Botao Li, coming all the way from the US, from San Diego. So a long journey. Thank you for being here. I hope you're not too jet lag and everything. So coming from Qualcomm Technologies, well, you probably know Qualcomm because it's everywhere. So he's a senior staff engineer. He's currently a senior staff manager working at Qualcomm in San Diego. Yeah, I said that already. He manages the EDA tools and design methodology for the company. So EDA stands for Electronic Design and Automation, right? Everything that goes around electronic software. Botao is also an expert in system-level modeling, FPGA, and software-hardware co-design. He has a bachelor's degree from Zhejiang University and master's degree from Michigan Technology University. Please welcome Botao. Thank you.
Thanks, Jan. Thanks for the introduction, and thanks for inviting me to Paris to meet everybody here and also to share our open source story with everybody. I heard a few good ones this morning. Yeah, thanks for sharing those interesting story with me as well. So I had some brief talk with a few of you during the early breaks, and I realized that there's quite a few guys probably not really familiar with Qualcomm. So I'm going to give a brief introduction of the company that I'm working for. So Qualcomm is specialized in telecommunication technologies and is headquartered in San Diego, California, United States. We have about 30K people around the world. We have offices in every big cities, pretty much. Even in Paris, we have 2 offices here, even though I haven't got a chance to visit them yet. In Qualcomm, we do wireless telecommunication technologies, and everybody here probably have a cell phone. Okay, so if you are using a cell phone, you must be using some kind of Qualcomm technologies. And most likely, you probably are using some of the chips designed by Qualcomm. So right now, in the telecommunication world, the buzzword is 5G. 5G is the next generation of telecommunication technology. Right now, what we're using is 4G. 5G is going to be better, it's going to be faster, and hopefully it's going to give us a better world. So 5G is what Qualcomm is focusing on. Better? Okay, no problem. Okay, so Qualcomm, a big high-tech company, as all the other big companies, we use a lot of EDA tools, including ASIC design tools, PCB design tools, FPGA design tools, RF design tools, and system-level design tools. So every year, Qualcomm spends a lot of money buying purchase licenses or lease licenses. So we are very cost sensitive. We are trying our best to reduce the EDA related expenses. That's why that we are looking to the open source community, because open source has been quite successful so far. Okay. All right, thanks. So open source is not really something new. Open source has been with us for 20, 30 years, and the most successful open source story probably is the Linux, the open source Linux. 20 years ago, Linux is, still has a very small market share. Even though it's an open source tool, that's still using the same term, market share. And nowadays, Linux is used everywhere. Okay, it's running workstations, it's running the clouds. And one of the interesting things that I heard is that, okay, Microsoft, they have a very famous cloud called Azure. And Azure is running on Linux instead of Windows. Yeah, it's very, very amazing. And also on cell phone, there's a lot of cell phone running Android operating system, and Android is built on top of Linux. So this is another success story for open source operating systems. Recently, I believe in the past 10 years or so, open hardware started to ramp up. And there's a website, some of you guys might already visit that website. It's called opensourcecore.org. And there are a lot of open source logic cores there. Like the first one, the OpenRISC, they actually taped out in silicons now. The other open source core is Amber, is ARM-like core. It's used a lot in FPGA, and I don't know if anybody here uses ARM core. And in the past couple of years, the RISC-V is really taking off. And the RISC-V is an open ISR created by UC Berkeley. And now there are a lot of companies develop open source RTL code or RTL core for RISC-V. Of course, today here we are focusing on the open source numerical analysis software. I hope that this specialized open source numerical area will follow the open source OS or open source hardware. Is going to be really successful in the future. For me, or for the company or the department that I'm working in, we don't really use Scilab a lot. The tool we use a lot is Octave, actually. I know here most of you guys use Scilab. Maybe a few guys used Octave. Can you raise your hand if you ever used Octave? Oh, cool. We got quite a few. Yeah. So Octave is a MATLAB-like software. We started to work with Octave open source community probably 5 years ago. 5 years ago, we want to reduce the EDA cost, so we looked into the open source alternatives. We evaluated quite a few open source tools at that time, and based on our special requirements, we choose to work with Octave. So in the past 5 years, okay, on one hand, we worked with the Octave developer, mostly John and a few guys working together with him. We give him feedback on which area of this tool should be improved and which are the components that are still missing. So we give them active feedback so they can improve the tool. So in the past 5 years, this tool is becoming a lot more robust, a lot more user-friendly. They have better GUI interface. They have better compatibility with the commercial tool, and they have much better plotting functionalities as well. So we are really happy with the progress this open source tool Octave has been made in the past 5 years or so. On the other hand, we work with our internal design groups. Okay, our design groups, generally, it's not easy to get design groups to switch to a new tool, and the open source tool could be even harder. So we worked with them to address the concern, to let them see the benefit of switching to open source community tools. And we also worked with them to, in some cases, to port the scripts or the design into open source. So there was quite a few success stories, and I will share one later. Nowadays, we have a pretty big Octave user community within Qualcomm. We see hundreds of people running this Octave software daily. So we looked back into what we did in the past 5 years. We think that there's a few important things that contributed to the success of Octave in our company. The first thing, of course, this tool is open source, it's free to use. And this is very important to high-tech industries because we are very cost sensitive. To switch to an open source tool makes sense to the program manager if you can save cost for the project. And also, it makes sense to the company, to the financial guys, because they need to write less money, less check out. So it's very important to make sure that the switching looks good in the eyes of the program managers and financial guys. And in Qualcomm, we do a lot of stuff. I just said, okay, we focus on communication, wireless communications. But wireless communications is used everywhere nowadays. It's not only used in mobile, it's also used in automotive industry, like telematics. It's used in wireless, and also nowadays the autonomous driving car. The autonomous driving car is using 5G. Supposedly, it's going to happen soon. Okay, so for 5G, right now there's a lot of companies working on 5G. Besides of Qualcomm, Intel is working on it. Samsung is working on it. Huawei is working on it. So the expectation is that 5G probably going to go to commercial use early next year. So somewhere, so it's going to be like 2019, early 2019. You probably will see some 5G-enabled phone in the market. And the large-scale launch of 5G is going to be 2020. So this is the industry expectation. So 2020, you probably is going to see a lot of 5G phones in the market. So 5G, it's going to play a really big role in autonomous. Okay, I diverted a little bit. Okay, let me come back to this open source software. And also, for open source software to be successful, it needs to make sense to engineers as well. Because engineers, we use the software. If it doesn't make sense to us, we are not going to use it. The least thing that we want to do, the last thing that we want to do during a tough project is to switch a tool. You don't want to spend a lot of time to learn a new tool or trying to change your design flow. So you want your design flow or your tool to be stable. And the good thing for Octave is that, okay, the GUI of Octave it's a very classic GUI. So engineers, there's no problem for them to pick up this GUI very rapidly. Myself, it took me less than 5 minutes to get familiar with the Octave GUI. Okay, another part is that Octave supports the most dominant scripting language in the industry. I'm not going to name the commercial tool. So it's not a problem for engineer to learn a new language. It's the same language they're going to use in Octave. So, which means they don't need to spend enough time to learn a new tool. Okay, in Qualcomm, I'm in charge of the system design tools. And one of the things that is important for me is that Octave supports all the operating systems. Because in a big company as big as Qualcomm, we have all sorts of machines, I mean workstations, and all sorts of operating systems. Like we have Windows, we have Linux, we have Red Hat Linux, we have SUSE Linux, we have CentOS, we have Mac as well. So these two works on all of them. This is very important in a big company because generally projects or engineers, they're going to share the code. So you want to make sure that this piece of code is going to run on every machine they're going to use. So this is important. Another part is that, okay, the tool is easy to install and administrative-wise, it's easy to do. Sometimes people think this is not a really big deal, but I've tried quite a few open source software, and one of the hurdles that I had to deal with is that, okay, you download the open source code, you have to figure out how to compile it. You have to figure out how to find all the dependencies, all the libraries that you are missing in your computing environment. And then you have to find out how to compile it and put it in the right location. That is a big hassle. And this Octave tool did pretty good on that side. So that's something I like as well. And as I mentioned before, now there's a lot of people in Qualcomm using this open source Octave. Here I'm coming to a specific example. Okay, we have a group of system engineers. They are doing Wi-Fi design. Okay, Wi-Fi is everywhere, and I believe the latest Wi-Fi that's commercially available is AC, and the next generation is going to AX. So they're doing this new generation of Wi-Fi. They need to do a lot of simulation. They do channel level simulation. They pass packets between the blocks and make sure that, say, the signal level is good, the error rate is it's well controlled, and everything looks fine. And do a lot of parameter sweeping, which means they have to look into a huge range of parameters and do a lot of simulation. And one of the engineers told me that, okay, if we use a commercial tool, put it into one machine, to get the whole simulation done, it's going to take 300 days. Okay, it's 300 days, imagine that. And of course, we are engineers. We find out ways to improve the speed. So the very classic strategy that we use is divide and conquer. So this group, when they find out it's going to spend 300 days, they went to the divide and conquer strategy as well. They cut the design into small pieces, thousands of small pieces. So instead of run one gigantic simulation, they run a few thousand small simulations. And in Qualcomm, we happen to have a LSF farm. Okay, so anybody heard of LSF farm? Okay, LSF farm basically is a machine cluster, thousands of machines. Those machines could be running different OS or operating systems. And we submit job to the server. So the machine in the middle, the lower part of the slide is LSF server. So you submit thousands of jobs to this server. And the server is going to look at the clients. So there could be hundreds of clients. And those clients could be running different OS. Of course, they look different, even though I'm using the same picture there, but they could be very different. So the server will look at the status of the clients and keep on dispatch jobs to those clients. So this system design team, they divided or chopped the gigantic simulation into small pieces and used the LSF to run them in parallel. And here you might be wondering, okay, this has nothing to do with Octave. Okay, let me explain why this has to do with Octave. Because if we use the commercial tool, we have to buy thousands of licenses. And there's no budget for that for this project. Okay. So instead of using commercial tool, they ported to Octave. They ported the source code to Octave. Okay. So Octave enabled them to run thousands of simulations simultaneously. So this is the important role that Octave played. Octave enabled this system group to get the simulation done in 2 days instead of 300 days. So good job, Octave. This is a continue of the example that I just talked about. And this is the simultaneous simulation running on the LSF farm by that project in the time range of 1 month. So this is a 1 month graph. The vertical is the number of simulation runs. So if we just pick one of the peak, let's say we can pick the first one if you guys like that one. So as you can see, at some point, there's actually about 1,300, I would say somewhere around 1,300 simulations running at the same time. And you can also see that each iteration, okay, which corresponds to each peak, takes about 2 days. So in the range of 1 month, they were successfully to run 1, 2, 3, 4, 7 iterations. So I guess before each running of the simulation, they must be modify the model and doing some code revision there. So it's a very, very interesting thing to see that Octave enabled this particular project to get the simulation done from 300 days to 2 days. And this is very important because, especially for wireless communication industry. Okay. Why is it important? Because wireless communication industry, the time to market is very important. The cell phone used to have a new generation every, let's say, a half year. Of course, now it's a little bit longer than that. But still, 300 days is just not acceptable. So Octave enabled this particular project to get to better time to market as well. All right, we talked about the good part of Octave. Now let's talk about the area that we think Octave should keep on improving. This is based on the feedback of all our design engineers that are using Octave right now. We generally go to each design group and meet them periodically and collect the feedback on all the EDA tools, not just Octave. We collect the feedback tools on other EDA tools as well. So based on the user feedback, we think those are the most important things that Octave should focus on. The first part is the speed. Okay, speed is important. Okay, let's take the previous example. Okay, if we can get the simulation done maybe in 1 day instead of 2 days, that'd be really good. Or maybe half a day, that'd be even better. So we do have some suggestions as to how to improve the speed, like just-in-time compiler. Okay, just-in-time compiler is very efficient for iterative compilations, which means, okay, Octave is running scripts in iterative mode. So instead of trying to interpret the code every time, okay, if there is any loop going on, you can compile the loop into native code. Okay, you can compile that into machine code if you like, and just run the machine code iteratively. That, of course, is going to be much faster. And the just-in-time compiler has been implemented for quite a few languages, like Java. They have just-in-time compiler there, and I believe Python probably has just-in-time compiler built in as well. So we think this is an area Octave probably can look into. The other part is to use some optimized math libraries, because math calculation could be very complicated, and there's still quite a lot of research going on in that area. So if we can use any or those new research results to improve the math computation, that should be really good towards improve the speed. The other area we would like to see Octave focus on is the peripheral features. Okay, so in the past 5 years, Octave has been focusing on the core features. So the core features now is pretty robust, and we feel happy about that. But when we talk with some of the design groups, when we recommend Octave to them, they run into problems. And those problems, most of the time, has to do with the peripheral features. Basically, in Octave means 2 boxes. So Octave, like Scilab, I heard that Scilab has 2 boxes as well. So Octave also has 2 boxes. And those 2 boxes are kind of specialized in different areas. Like we have signal 2 boxes, statistics 2 boxes. So the functionality of those 2 boxes are not that great yet. And the designers, if they do want to do some specialized signal processing, they probably couldn't find the function they want, and so they were hesitant to use Octave. And here are the most important things that we think it's important for my company. Okay, your company probably, depending on which industry you are in, you might have a different idea. So for us, we think signal 2 boxes is very important. It's the basic for all the other 2 boxes. And the statistics is very important because statistics, it's used a lot for machine learning purposes. And optimization, image processing, control 2 boxes, those are other ones that we would like to see got improved in the next in the coming years. Okay, the last one is to it's actually how to get more users use Octave tools. The reason here is that, okay, if there's more people using this tool, if there's any bug, it's easy to be spotted, okay? And also, if there's more people using this tool, there'll be more, there'll be more push to get new functionalities implemented. And also, if there's more people, there's more users use this tool, it's easier for the open source community to get additional resource to develop this tool as well. So I think like this morning there's a presentation mentioned that in India there's about 300,000 students got trained on Scilab. So this is really good. So we would like to see that in the future that Octave will be used in college classes as well, and get all the kids, all the college students using Octave. We found out that, okay, if a college graduate, if he uses a tool in college classes, the chances is that he's going to use the same tool for engineering work. So if the colleges students got trained in Octave in the classes, chances is that they're going to use it when they join the companies. So that's why we think we should put more effort into that area. And also, we hope that Octave in the future will get more exposure in major conferences. I know this is this conference is focusing on open source. This is good that we coming together, we share idea, and we share stories, and we share the directions that we should push forward. But it's also important that we go out of the open source community. We go to the big conferences that has all the big players in the high-tech industry, and got more exposure there. So so overall, I think Octave, it's a very successful story so far for us. And in the future, hopefully we will have more successful stories regarding open source tools to share with you all. And also, hopefully you guys will have more successful story to share with us as well. So this concludes my presentation. Thanks.
Thank you, Botao. Do we have questions, maybe, from the Scilab audience? Okay, maybe we'll keep it for the Q&A later.
All right.
Thank you very much. So our next presenter, I think I have printed it out. Jean-Claude Boulet from INRA. So Jean-Claude is a PhD at INRA. He's a chemometrician. Yes. He will tell us everything about it. So he's responsible of chemometry at the polyphenol. Okay. Yes, polyphenol platform. Polyphenol analytical platform in Montpellier, right? Yes. Montpellier, I know. Well, he's a leader of CheMooCs. It's a MOOC on chemometry, just as it implies, since 2016. So you will tell us about embedding Scilab within Galaxy.
Thank you, Jan. Before beginning the presentation, I would like to tell you a few words about INRA. Everybody maybe don't know what is INRA. So INRA is the French National Research Institute in agronomy, that is agriculture, food, and byproducts from agriculture. And we are about 8,000 people in France. So Jan presented chemometrics. So before going to the presentation. I also wanted to present what is chemometrics. In fact, it's very, very simple. Everything begins with a signal. You have such a signal on the left of the slide, which is here a spectrum, a near-infrared spectrum. And for someone who looks at the signal, it means nothing. You can get no information about such figure. And all the job of chemometrics will be to extract information for this type of signals. These signals where all the variables are highly correlated. Excuse me. So we will try to extract information. There are two types of information. You have two types of. We are going to build models which can be either regressions or discriminant analysis. Regressions are based on information where quantitative, for example, the sugar content of an apple. And so we build models to predict in apples and different fruits the sugar, the acidity, etc. Qualitative information will be applied with discriminant analysis. For example, we will try with the near spectrum to separate golden apples from starking apples. Or it can be in the street, it can be also a good product versus a bad product. So you have very shortly an idea about what we plan to do. We do models for such applications. So I belong to a group of chemometricians, and a few years ago we decided to create a MOOC. So a MOOC, it means a massive open online courses. So everything is in the name. These are courses that you can follow directly on the internet. They are free. No need to pay. And our MOOC about chemometrics is on fun for France, Université Numérique. So the last one has just finished yesterday, but there is another one on which we will begin next February. So if you want, you can register on fun slash well, you can ask me the address after. fun-mooc.fr. Yes. But you can also find other MOOCs. Unfortunately, for some of you, it's in French, but we all agreed that our level in French, in English, was not enough to do the MOOC in English. So we did it in French, and it's a big job, even in French, to build a MOOC. So here are the different units. You have different universities, high school in France, research institutes that have collaborated to this MOOC. And we represent almost all the French community in chemometrics. So it's a collaborative project. It's not my project, it's a project of a group of people. So the aim of the MOOC is to bring some knowledge to people. And in the MOOC, I don't detail the MOOC, but we will ask for the students to learn about the chemometrics, the different tools, how they can be tuned, but also they must have some knowledge about the mathematical consolidation, linear algebra, dot product, etc. So there is a lot of learn to when you follow such a MOOC. So the MOOC provides the knowledge, but we needed also a tool to do exercise, to practice, of course, because we work on data, hundreds, thousands of variables, so we needed a tool. We had such a tool. We had such a tool because some years ago, I had made an atoms module named FACT. It was in 2013, 5 years ago. So this atom modules is dedicated to chemometrics, and you can see here the window with almost 40,000 downloads since 5 years. It's not been updated since 2 years because I'm waiting for next update of Scilab, the Scilab 06602. I'm waiting. So we had such tool, but it's not. There are some issues. The first one, but it's a general issue for all situations, and no exception to it. That is, with one language, you don't have all the functions that you need. Every time you have a function, something interesting that you will find in another language. So that was the first problem. The first problem was that during the MOOC, we asked people to learn about mathematics, chemometrics, and we could not ask them to learn also programming. Those are two things different. There would have been too much work. But in fact, with Scilab, we use line commands. Here you have the example on the right of PLS regression. So you have different variables, but you must know what they mean in order to run the function. And that was is too hard to learn for the users of the MOOC. They are almost all of them. They have another job. They are biologists, technicians, etc. They want to learn chemometrics, but learn a language, no. Yes. And so we found the solution with Galaxy. So Galaxy is a framework. I can call it a framework. You can find it at galaxyproject.org. It was made first for genomics, metabolomics, etc. But we downloaded the Galaxy from this site, and we built our own instance of Galaxy, which was called ChemFlow, which is a web application that is you can access to it directly via the browser, Firefox, for example. And on the left, you have the address of our site. It's all free. The MOOC was free. The software is free. So if you have smartphones or laptops, you can connect. You can create your account, and within 2 minutes, you can begin to work to process data on ChemFlow. Here is an example of a window. Previously, I presented the command line for the PLS regression on the left. On the right, we have the Galaxy window, much more complete. Yes, much more information. So if if you come back to CameFlow Galaxy 6 months after your last time you used it, you are able to remember all of it. And so it's easier for people. They know they know how to fill each field. For example, you have on the left you have the 4 and 10, and you can find where they are on the left on the right window. Excuse me. So no more line command for the users. Is it complicated? I would say no. It's a Galaxy. It's very very simple. The first step is, of course, to install Galaxy. You can download it from the previous address. You can remove all the tools that don't interest you. You have to configure some configuration files, but not lot, 2 or 3, no more. Create wrappers, XML. So it's easy. It's easy to make the wrappers, and you also need to have, of course, some tools to wrap into Galaxy, and what we did in CameFlow. Here is an example of a wrapper. So you can see on the top some requirements about the software. Here it will be Scilab, but it can be another software. You have the description of the input for the tool. Then in black, we will send the wrapper will send a script to Scilab for it to be run, and then on the bottom of the script, we have the output that will be sent back to Galaxy by Scilab. So you see that it can be very easy to wrap, and it can be also wrapped in other languages. So here are the 3 languages that we use in CameFlow, mainly Scilab for most processing, Octave for some toolboxes that were big, too complicated to write, and we didn't want to write them in Scilab, and we use also R for some graphical presentations. But we could also wrap tools in Python, C, PL, Java, and in fact, what you want. So it's a very, very interesting. It's very interesting because the first interest is that we can recycle code without any problem. You can pick up a tool in Scilab, another in R, a third one in Octave, and all of them will be in Galaxy, and for the user doesn't know which language runs behind Galaxy. So we can create a synergy between languages. No more line commands for the users. It's easier. We can exchange data. That is a particularity of Galaxy, and also we can build a workflow with such tool. So we have this software. So for looking forward, our main problem now is to think about a data set format, because we use right now we use CSV and MAT files, but it's not good for the new data that are coming, which are much larger data. I would say big data, but there may be a confusion of big data. For me, our data are big because one sample is big. One sample, one analysis can take hundreds of megaoctets. So we can have 10 or 100 samples, and so easily you have a teraoctet of data. So we thought about HDF, And I was pleased to discover finally that the Scilab was based on the HDF5, and I think that it's a pretty feature of Scilab that should be put forward, because I think that the HDF format will be more developed later. I already use it in a second instance of Galaxy, because in fact we have two instances of Galaxy, and I use it on the second one. We want also to add more method in CameFlow in order to be able to benchmark some methods. That is often interesting, because when someone provides a new method, it's interesting to compare it to existing method. The only problem we have is the funding, because as everything is free, the MOOC is free, the CameFlow is free, so we don't have money. So we rely on sponsorship and some gifts. So if some of you have some money to spend and don't know how to spend it, they can think to us, or many to us. I have a short presentation. My presentation is short, but I will show you Galaxy on live. So here is our Galaxy here. How minutes do we have? 10 minutes. Oh, it's enough. So here is CameFlow. On the left we have the different tools. So for example, all the pretreatments, all the regression, discrimination are Scilab. Multi-way, multi-table analysis, Scilab aussi. Most of them are Scilab. Curve resolution it's a MATLAB code, but which is run here on Octave, and the plots here, and the plots are made with R. So, but here you cannot say. Cannot guess that. I would just will run, for example, a regression. Is here the PLS, which is because it's very often used. So here I just have to choose my data. The X data is the spectra, so the near infrared spectra. The Y data is this one, values of triglyceride. I can choose in this data one of them. The algorithm, the cross-validation, centering, etc. I want to modify. Centering, yes, no. And here I have the results on the left. Good. Is it good? And I can see here the RMSec and RMSecV in order to determine the number of the latent variables of my models. So you can see it's very easy to use, but we can also realize the workflow. So I prepared one workflow for you. ScilabTec, yes. So here's my workflow. It's almost the same thing that I've just done. That is an input, first input spectrum, second input values, triglycerides, for instance, and I perform a PLS. But here I would like to add some pretreatments. So I'd like to add a detrain. So I want to detrain the spectra to correct the baseline and to translate. And I want to add a normalization to my spectra. So I add here the CNV. So I must modify the links here. So I remove this one. I just have to link here. You can see that it's very easy to make a workflow. So here it is. So my spectra will be first detrended, correct the baseline, normalized with SNV, and then sent to the PLS with here the Y data. So before I will save, and then I can run the workflow. So you can see here the trend SNV. I won't modify the parameters, but I have here to precise the inputs. So here the triglyceride, okay, and I run the workflow and just wait a few seconds. It won't be long. And so so now we have the results, and we should have the same results. Not exactly the same, but so you can see some results of the process. Okay, that's all. Thank you.
Thank you, Jean-Claude. Thank you. So, do you have any question for Jean-Claude? Maybe later. Maybe later. Thank you very much for your presentation. So, next presentation before the break is from David Müller from the German Aerospace Center, DLR. He's a research scientist at the Institute of Flight Systems of DLR, working with the air vehicle simulator operated by the Department of Flight Dynamics and Simulation. He received his Master of Science in Aerospace Engineering from the Technical University of Braunschweig. His research interest lies in the improvement of pilot aircraft interactions by way of assistance systems. During his work for the EU project Argo, he received the award Best of Track Human Factor at the Digital Avionics System Conference in 2018 in London for the paper Enhanced Functions for a Parallel Multicore Ground Proximity Warning System. Did you send me your presentation?
I sent it, but I also have it here, so.
I'm going to use this one. This one?
Yes.
Right.
Okay, thank you. Let me just. Awesome. Okay, thank you for your introduction, Jan. And actually, Jan told me that there might be some listeners from Japan, so konnichiwa, minasan, if that's the case. Yeah, so my talk is entitled Towards Model-Based Design of Mission-Critical Avionics using ScilabTec, and I'm going to tell you about the work that we did for the Argo project using XCOS to develop a terrain awareness and warning system. So the outline of my talk is that first I'm going to introduce to you what we call the fourth revolution of aeronautics and the challenge that emerges from it, and also the answer to this challenge that is proposed by the Argo project. The main part of my talk is obviously about the work that we did, about our use case for the Argo project. So I'm first going to tell you what terrain awareness and warning system actually is, and give you some examples of the implementation and how we did it with ScilabTec. And at the end of that part, I'm going to tell you about our user experience that we had during this endeavor. Then I'm going to come back for a moment to the Argo project and tell you about the workflow and about the X-in-the-loop testing endeavors that we did in order to verify our software. And in the end, there's a very short outlook for you. So if you look at the history or the evolution of aeronautics, you can identify 4 revolutions. The first revolution, which happened around the 1900s with Otto Lilienthal and the Wright brothers, was moving on from flying machines that were lighter than air to machines that were heavier than air, and actually making them fly and being successful with this. The second revolution came, let's say, around the time of the Second World War, with things like electric drives in aircraft, hydraulic actuators, and also the arrival of full metal airframes, because before you had quite a few airplanes that were wood and fabric and not metal. The third revolution came around the 60s, 70s with the arrival of digital avionics systems and the glass cockpit. And right now we are at the cusp of the fourth revolution, which we call the smart and connected flight. So we have technologies like the ADS-B, which is the automatic dependent surveillance broadcast. And this is a thing that enables aircraft to talk to each other or to ground stations without the pilot even being involved. So that's why it's called automatic, obviously. And the challenge that emerges from this is quite obviously the increase of complexity. So if we look at these figures here, in 1974, Lockheed Martin built their F-16 fighter aircraft, and it featured 135,000 single lines of code. And if we jump to 2012, the very same company built the F-35 Lightning II aircraft, and I mean, it's quite obvious the rise of the single lines of code has been exponential. And this trend is also true for civil aviation. There are some numbers by Airbus here. So you can see that obviously complexity is growing and the trend will continue like this. So it was very soon clear to the engineers that the big challenge is to deal with this complexity by and at the same time not to sacrifice safety in dealing with the challenge, but also to boost your the productivity in development and to increase your product performance. So as I said, engineers realized this, and there were some projects in the recent years. You see, when in aviation we talk about recent, it's usually a bit longer than, let's say, in the automotive industry, because everything is more long-term. So in 2012, EADS Innovation Works, they thought about the utilization of multi-core systems in partitioned environments. In 2013, Cassidian considered the application of multi-core architectures for a degraded vision landing system for a helicopter. In 2014, Thales thought about design principles of predictable and efficient multi-core systems to meet embedded computer requirements in avionics. And also in 2014, Saab Aeronautics were thinking about ways how to guarantee determinism for avionic applications when they are running on multiple cores and interact through a shared memory. So what all these efforts have in common, that they concentrate on the applicability of multi-core platforms regarding the safety constraints of the avionics domain. Safety is always a very big issue, but what they didn't consider was the development methodology. So I talked about boosting the productivity in development, and none of these efforts were actually looking at that. So how to do this, how to boost the productivity? We think, and considering the rise of the modeling and simulation-based approaches, many other people think so as well. The modeling and simulation-based approaches are the key to this question. So
just to explain it to you, what you do is that the controller or the system that you want to develop, you first create a model of it, you create a model of your plant, and you put the two of them together and do model in the loop testing. Once you are confident that your model works correctly, you generate code from it. And this code is then applied to software in the loop testing. And if you're then confident in your software, you can put it to the hardware and put that to the market in the end. So now the question is, how can we put the two together? How can we apply the modeling and simulation-based approaches for multi-core systems? And this is where the Argo project enters the stage. So Michael has already talked about it this morning. So I'm not going to go into detail too much, just telling you that our role in this project was to develop a use case, which is a terrain awareness and warning system that we would develop using the Argo toolchain and then integrate it into our air vehicle simulator that we run at the Institute of Flight Systems at DLR. So this, the air vehicle simulator is called AVES, so I'm going to talk about it using the name AVES. But what is a terrain awareness and warning system? It's an advisory system, a supervisor, that creates visual and oral warnings in order to help the pilot avoid controlled flight into terrain. Controlled flight into terrain, or short CFIT, means that an aircraft crashes, but not because something's broken or something's not working, but because the pilot is simply not aware of the crash that is going on right now. So this is actually it's one of the three primary reasons for fatalities in civil aviation. So it's a huge concern to avoid it by all means possible. So these warnings have like 5 basic modes. Mode 1 warns the pilot if there's an excessive descent rate, so if you're just sinking rapidly. Mode 2 warns you if there's excessive terrain closure rate. It means that like a mountain is rising beneath you and you're kind of coming too close to that mountain. Mode 3 warns of altitude loss after takeoff. Mode 4 is, you can describe it in a way that the system looks at your current configuration and says, okay, you're pretty close to the ground and you don't have landing gear or landing flaps extended. What are we actually doing down here? This is what Mode 4 does. And the Mode 5 warns you if during an approach you're too far below the glide slope, when you're coming in too low. These are the basic 5 modes of the system. There are also enhanced features, like for example the terrain awareness and display. These kind of functions rely on a terrain database. And what the terrain awareness and display does is that it provides an image to the pilot of the surrounding terrain in a color coding, and it also looks 60 seconds into the future and tries to decide if, like on the projected flight path, if there's any terrain interaction on there, and warns the pilot of that. So this is the system that we decided to develop, and we went about doing it in the way that. So I mentioned that we have an A320 cockpit in AVES, and we have that cockpit because we also have the corresponding airplane to that. So DLR runs a modified A320, which is called ATRA, the Advanced Technology Research Aircraft. And this specific aircraft is equipped with an enhanced ground proximity warning system by Honeywell. So EGPWS is the commercial name of this system. With the ATRA, we got an FCOM by Airbus, which is the Flight Crew Operating Manual, which is a pretty thick book with all the stuff that the pilots need to know, and it has one chapter about the EGPWS, and we use this chapter and the behavior that is described there to imitate the behavior of the real system and develop our requirements from that. The other requirements were determined by the interface and the infrastructure of our simulator. So I'm not going to go into too much detail here in this slide. Only the important thing to have you know is that the heart and brain of our simulator is the, I don't know if you can even read this, it's the interface computer, because every other module, or like all the other modules, they talk to each other by way of the interface computer, hence the name, obviously. So the idea for the use case was just to take the designated target platform of Argo, which is an Aurix TC297B evaluation board. And just like the other modules, just hook it up to the Ethernet bus and have it talk to the interface computer, and by way of that to all the other systems that it needs to talk to. So yeah, about the controller modeling in Scilab XCourse. This is an overview of the system, so you can see that the 5 basic modes and also the terrain awareness, they work in parallel. So there are no interdependencies, and they all talk to the data output management, which enforces kind of like a prioritization of all the alerts that you could have probably at the same time, and just makes sure that the pilot is alerted of the most critical situation. So a terrain awareness and warning system is, as I said, a supervisor controller, so it doesn't act on its own, but it warns the pilot. So we don't have any control loops or anything, but we just do a lot of like logical operations on the signal. So just to let you know what kind of blocks we use, we have the very common ones like the logical and relational operators, dynamic switches, delays. We have some very basic maths going on, and some not so basic maths like the interpolation and the two-dimensional interpolation block, matrix multiplication, and others like the logic table or the sci-func block, where you can put sci-func, Scilab script functions into your XCOS model. I wanted to give you an example of how we actually implemented the modes. The mode 1 is pretty much one of the most simple ones. So the idea behind is that you have one parameter, like in this case a rate of descent, and you consider a limit altitude, which is implemented as a function of these in this case the rate of descent. So if you look at this orange aircraft here, like the limit altitude for the second boundary for the pull-up warning, we are obviously above that, so there's no problem here. But we are below the blue boundary, and so the pilot will get a sync rate warning from this, because in this interpolation block here, we give the vertical speed, the descent rate, and the limit altitude that comes out on the back here is then compared to our current aircraft altitude. This is the basic principle for all of the other modes. Of course, they're not all that simple. So this is mode 4. It looks a little more intimidating, I say, but I'm not going to explain it right now. It would take too long. Instead, I want to mention a little bit more about the enhanced functions. So we didn't implement them in XCOS, but instead we wrote some Scilab scripts that we put into the system, and just some data. So as I said, these functions rely on a terrain database, and this terrain database has it has a resolution of 3 arc seconds, which is roughly 90 meters between the points in this database. And the collision detection works in 2 phases. We have the broad phase, where you extract a uniform grid out of the database that is visualized here. This is the way how Scilab would plot it. This is your area of interest, basically. And then in the narrow phase, you do the color coding, and you also check if there's any terrain interactions with your flight path in the future. So to mention the plant modeling. So we didn't use the real A320 model that we run in the simulator, which is done in Simulink, but instead we had a pilot. We had a student implement a simplified version of this model in XCOS, and this is what you see here. So you have the forces and moments, the equations of motion, and the important thing is that the outputs here is what is then fed into the GPWS model that we created. So about our user experience, there were many things that we liked about XCOS. So it wasn't too much of a problem. For me as a student who, like many other students, worked with MATLAB Simulink during university, it wasn't too hard to switch to Scilab. Still, we do have some things that we would like to see in the future. And I talk from the perspective that we have many colleagues in our department or in our institute who are very skeptic and who would want to see some things being done before they could, yeah, let's say even imagine of to switch to XCOS. So one thing is the scalability regarding the number of blocks, of levels, of subsystems. We looked for some numbers and we found a standard from the automotive industry from 2012 saying that for a complex model you could easily have 15,000 blocks, 700 subsystems and 16 levels. And I don't want to scare Clément, but our Simulink model of the A320 is a tad bigger than this. So actually, I'm not quite sure how big the EGBWS model is. It's obviously smaller than that, so there's no problem here. That's what I really want to express as well. We didn't have a problem with EGBWS, but as I said, for our colleagues to be willing to adopt Scilab XCOS, we really would need to push the boundaries of the scalability here. Also some things about the usability, or maybe even the reusability. Managing data flow is a pretty important thing. So I don't know if you have ever tried to use buses in XCOS. We tried it. And sorry, I forgot to mention, we are still using Scilab 552 because we started with this in 2016 and we haven't migrated ever since. So we just hope that things will be better in the later versions. But yeah, so in 552 we tried the buses and it just didn't work out too well for us. Another thing that we would like to see is the model referencing libraries or toolboxes and legacy code integration. Like with the toolboxes that we have in Scilab 552, we don't feel they are really that user-friendly as of yet. So might be better in the future. And also the automatic layout of models. This is a nice to have thing, but yeah, we still thought we'd mention it. So as promised, I'm going to go back to the Argo workflow. So as we have gathered from my presentation right now, we start with an XCOS model, obviously, and you generate Scilab script from this model with Scilab as the front-end tool. What is then done in this next phase is that the Scilab script is transferred to a sequential C code, like conventional C code. But in addition to that, you get a lot of pragmas that will help in the next step with the parallelization. And this is it as far as we as end users are concerned. But obviously, there's a lot more going on behind the under the surface of the Argo project. But yeah, as I said, we as an end user, we just want to use Mtrix Parallel Studio, which is the tool that has all the functionality of the toolchain being like combined in it. And we just want to use this and be sure that at the end we get parallelized code that is worst case execution time aware and that runs on the target hardware that we specified. So in this case, as we have the Oryx TC297B, it's a 3-core system, so 3 cores. And the way that we implement it is that on the first core we have all the communications, the Ethernet stuff running, and the GBWS actually runs on the 2 other cores. So just to give you a quick view of how the tool looks like. So, and finally I want to talk about a little bit about the X-in-the-loop testing. So this is the conventional approach, the conventional process for the model-based design. So even in the design phase, when you do your when you design and build your controller model, you can even then put it together with the plant model and already do some testing, the model and the loop testing. And as I mentioned in the beginning, once you're confident that your model is doing well and is functioning correctly, you can generate code from it and put that code to run in the software and loop testing together with the model. Then we are at this stage here. Once you're confident that the generated code is also correct, you can then put it on the designated processor and run it on an evaluation board, again, together with the model. And finally, in the end, you can put your software on your hardware that you want to use or that you want to have as a product in the end, and run the hardware and the loop testing in this stage. So for Argo, it's a little more complicated because we have one additional step of, or actually we have two additional steps of code generation. We have the step from the model to the Scilab script, and we have the step from the sequential code to the parallel code. So for all these three steps, we had to conduct testing in order to make sure that during none of these steps, any functionality was lost or any errors were introduced. So we had to rely a lot on closed and open loop testing to make sure that nothing went wrong. Just to let you know what the difference is between closed and open loop testing. So Kana defines a closed loop or scenario testing as testing of a credible story, like something that in our case a pilot would encounter in the real world. So you have to specify a scenario with all the different aspects, like in an aircraft. This is really a whole lot of aspects that you have to define in the beginning. And you execute the scenario by running your plant and your system under test together. And you get outputs, and you compare these outputs to the ones that you expected or that you defined in the beginning. So for the open loop testing or the unit testing, there's two ways that, how you can end up doing open loop testing. First, if you, like we did this with all the basic modes, we ran all the basic modes in unit testing in the beginning. But another thing that can happen is that you find a mistake or a bug in your whole system, and you track the bug down to one specific part of your system, and then you can do unit testing with this part. So instead of defining a whole scenario, you define a test vector with the time, the input variables, which is a very reduced set of input variables. This is one of the good points about unit testing. Maybe there are some state variables, and again, you have expected outputs, and you check your results against the expected outputs. This is what we have been doing already with Argo, and the final thing that is left to do, and this is scheduled for mid of December this year, that we are going to put the Oryx board into the Avis infrastructure. We have it run in the cockpit, and we have our A320 pilots come and fly the aircraft with the system, and ask them about if this is how it feels in the real aircraft. And this is the final step for us in the Argo project. So this also brings me to the end of my presentation. Thanks for your attention, and I'll take any questions unless you want to have coffee right now. So thank you. Okay, there's a question there.
Thank you, David. So we can have a small break. It's one last chance for you to get together, to exchange around Scilab, and afterwards a few more presentations, and we'll be soon closing the day. So thank you for those very good presentations, and see you in 30 minutes. So for those of you who might want to take the airplane at Roissy-Charles de Gaulle, there's a problem with the area. So you might want to check how to get there. So it better be through the taxi. I think there's no local train driving over there. So we have 1 hour left of presentations. The last presentations from our speaker is from Manuel Tobias. Could you help me pronounce that? Chapo, from the University of Applied Science of Esslingen as a joint project with IT Designers Group. He's a student in computer engineering since 2015. He's performed in 2017 an internship at FNS Electronic System as embedded system developer and currently working as a student employee at the IT Designer Group. His focus is on modeling and simulation and coding in NIM and embedded system.
Thank you, Jan, for your introduction. Thanks to all the speakers so far for your insights and projects, and of course thanks to all of you for being here and being patient, because I know it has been a long day, lots of presentations. So I just want to present you what I've done for the last 3 months. It's an implementation of a converting toolbox for Scilab, and it's focusing on transforming figures and graphics from Scilab to the TICS LaTeX environment. And first of all, I have a question. Does anybody in this room know what LaTeX is or has maybe used it recently? Ah, okay. Oh, nice. Well, that's good. So I don't have to explain it. For those of you who do not know what it is, it's similar to Word. So this should do it. So first, what's the motivation behind another toolbox? The point is, sometimes in your scientific papers or articles, you have to include graphics and figures. And as some of you may know, sometimes it's mandatory to hand in LaTeX documents for some journals. They won't even accept anything from Word. So we need something to do this, and usually we can just grab a PNG image or a JPEG image, and Scilab does provide functionality for converting this. But there's something else called TICS, and MATLAB and Octave do yet provide this. I think in Octave it's a built-in functionality. MATLAB has packages like the MATLAB to TICS package, and Scilab does not. So the idea was to create this toolbox, and I did indeed create a toolbox prototype. I called it XS to TICS because this is the naming scheme used in Scilab for conversion functions. And the project idea itself was initiated by Professor Dr. Koch, which is among us today. So first, my agenda. I will tell you something about my working environment, a little bit, just not much. And of course, I will explain in detail what's LaTeX and the use and the package I used for plotting with this, which is called PGF plots. And of course, I will go more into detail about the converter toolbox itself, give a small example, and then of course, tell you something about new features and the advantage so far. So I'm a student from the University of Applied Science in Esslingen. It's located near Stuttgart. We have around 6,000 students in different majors, especially engineering, like software and mechanical engineering, automotive systems, and of course some social work students. And the university itself has many cooperations with companies around Stuttgart, for example, Porsche and Daimler. You should know these. And for the university technology transfer side, there's something called the Steinbeis Transfer Center. And you could compare it to the Fraunhofer Institute, just for University of Applied Sciences. And in fact, the IT Designers Group, where I'm working as a student employee, was founded by a professor from my university, Dr. Joachim Goll, which initiated this company as a project via the Steinbeis Transfer Center. So they have today they're a really big company with 200 employees, but 50 of them are like students, so they are really they are like highly integrated in the university life, and they develop personalized software for different sectors like the automobile, finance, and logistics sector. And of course, they also provide another thing which is called the application lifecycle management. And this basically is important if you, for example, want to use software or something in a special project like in the automobile branch, and you want to keep it updated, you want to keep it alive, and of course you want to keep it working. So this is the working environment. Now we'll tell you something about the target software. LaTeX is commonly known, I guess, but I still tell you it's a typesetting language, and you could compare it to like HTML, because you also use coding fragments to set your document. And the important part is it's open source, so it's a nice addition to Scilab itself. And the package we're using for the toolbox is PGFplots, which is a plotting package based on PGFTix. I will also tell you what's this later on. LaTeX itself is widely used in the scientific area. So if you have ever written an article, or if you have might read other articles from other researchers, you might have grabbed some kind of LaTeX document, or at least use the generated PDF. So LaTeX is well known for its typesetting of mathematical formulas. It's so good that even Microsoft Office used this. The principle of LaTeX is that you should focus on content and not the design. So this is very opposed to the idea of Microsoft Word. And as you can see in the gray box, there is a small example. Pretty simple. You have a specification for the document class to use. You can, for example, use article, books, even presentations are possible. And of course, you can just set like titles, authors. There are even blocks for lists and other structural elements. And of course, you have these begin and end blocks, which are very important. You will see this later, maybe, in the toolbox. And yeah, with this simple instructions, you could just create a nice-looking document with the title and an author. So, but this is not all, because if you want to use graphics, we need something to for plotting. So they're used PGFplots. This is a tool where you can do simple two-dimensional or three-dimensional graphics, and it also supports logarithmic plots and scaling. And in the gray box, I think it's a little bit small, but you could see a simple example about plotting. It's also like you have the axis elements, you have coordinates to add, and you can do fancy-looking graphics with it. So the last thing we still don't know yet is PGFTix. This is some kind of also typesetting language for graphics, because LaTeX itself do not support graphics. The point about PGF is it's low level, and TIX is more about high level graphics. So the image you can see is an example which is made in TIX itself. You have a fancy looking graph with labels all over it, even a cloud in the background, and it would be way too much to just use TIX for a converter toolbox, because we do not need this kind of graphics in Scilab. So I just stick to PGFplots. So the converter toolbox itself, I have an image included in this slide with how the graphics are represented in Scilab itself. They are in some kind of tree hierarchy, and at the top level you can see there are the figure element. It contains basic attributes like the figure size, the used color maps, and if you want to go to the next node, the axis elements, you could either use the children element inside this figure, or just use the get and set methods in Scilab itself. In the image itself you can see, I guess they are the C or Java functions, because I took this image from the Scilab wiki. I'm not sure if this is still still a current representation, but as far as I has tested this with the toolbox, I guess it is. So the point is, the first step in implementation was looking what's out there, and I found the MATLAB2Tix package. I looked into it, and I found out that it has way more functionality than needed. For example, there's a kind of option parser inside. So if you want to convert a graphic, you could also add additional legend entries. But if you, for example, if you run a simulation and you want to convert the result to a nice-looking Tix graphic, you don't need this because you can just rerun the simulation itself and change it beforehand. So the other point is that this package is provided as a single file, around 7,000 lines of code, 100 unprecise declared functions. For example, the save to file function inside does not save anything to a file, but does the gathering and generating of strings itself. So it just abandoned the idea of just trying to convert the MATLAB2Tix package to Scilab itself, but rather took the basic ideas about which are gathering all the graphic elements, parsing them to the Tix format, and writing them to the file. So we also provide this as a toolbox, this functionality, not just as a function file itself. And of course, it should be solely written in Scilab, because then we don't have any C or Java issues. And I ended up with the 3 functions below, the gather graphics attributes, the generate Tix strings, and access2Tix function. The first 2 are the functions which are gather all the graphic elements from the tree hierarchy, and the second are the second function just translate these to the Tix format. And to not confuse the user with a complicated toolbox, I just wrote another interface called access2Tix, and this is the main function you should use in the end. Graphically, by the way, this image is done in Tix itself, and it took me around like 5 minutes to do this. So on the left side you have a Scilab figure represented by the handles. If you call the access2Tix function, first the gather graphic attributes is called, which yields an attribute struct. Then the generate Tix strings is called, which yields the Tix strings itself as a vector. And then I just call a save to file function to generate the text file. So these next few slides just go into detail what each function does. As I told you, the gather graphics is for gathering the graphic elements, so we have to traverse the graphic hierarchy, we have to collect all necessary attributes like figure size, color maps, the element of axis inside, the element of lines, and of course create structures or cells for it, and just return these as an attribute struct. The next step is for the generate Tix strings, we have to add all necessary environment information. In the beginning you saw there was something like begin document, begin Tix picture, end document, end Tix picture. We have to do this in this function, and also we have to add all necessary access. And for the current state of the toolbox, we just generate the plots from the polylines. So in action, it should look like this. You could just cd into your toolbox, you execute the scripts. Later on, there will be an atoms package, so you can just use it right on. And then, of course, just call the access2Tix function. The first parameter is the file name itself. The second just states if you want a standalone or embeddable file. This is important, for example, if you want to write a book in LaTeX, you would not just write one single file with all chapters in it, but you would rather use directory structure with chapters as directory, and in each of it would be like the pages or sub-chapters. And of course, for the images, you may want this same feature to just add the file as a separate command and not like use it as a standalone. So in the end, it's like this. On the left side, you have the Scilab figure. It's just a simple 2D plot with some sinus and cosinus functions. And on the right side, you have the result created by the access2Tix toolbox. And as you can see, the fonts are nice looking, and even the image is a little bit more smaller. At least the markers, but this could easily be changed in TICS itself. So the current state for the converter toolbox is that the toolbox structure is mainly done. We have the macros, we have some tests, we have help pages. So whenever you should use this toolbox in the future, you could just type in help access to TICS if you're not knowing what you're doing. And of course, basic conversion for 2D figures, but currently just simple 2D line plots are supported. And of course, we can add titles, legends, standalone files, and so on. So the advantage created by this toolbox now is that we have files that are editable after conversion. This is important because if you, for example, just convert a JPEG or PNG image, and you want, for example, to change the font style, you have to rerun your simulation, which might be okay, but if you have, like, for example, 100 of graphics, this would not be nice. And the next point is that we have the same quality and of appearance as in LaTeX. As you have seen before, the image on the left looked a little bit crappy, which the point is it's depending on the operating system and the environment you're using. And we do not want this in our LaTeX file. And also important, if the file is editable, it should be use the same structure as LaTeX, because if you're familiar with LaTeX, you do not want to learn another tool. For example, you don't want to jump onto GIMP or Photoshop to change your images. And the last but not least point is it elevates Scilab on the same level as MATLAB and Octave. The Octave part is not so important, but yes, to compare it with MATLAB, I guess it's a good point. So the next steps for the implementation process is to make subplots possible, because now we just have like simple 2D plots, and not even subplots are possible. And of course, the string generation to this date is a little bit like just add all begin and end lines, and of course at the axis and the polylines. But in the future, I would support 3D functionality for the surface, histograms, and all the other graphic objects possible in Scilab. This can easily be done through the addplot3d command from pgfplots. And of course, more robust testing is needed. So this was the end for my presentation. Thank you for your patience. If you have any questions, you can ask me now. Yep, there's a question.
Implemented in the new version of Scilab?
Yes, indeed it is. Yes? No, not yet. The toolbox structure is there, but it's not published yet. Yes, definitely, but not this year anymore.
Thank you, Manuel. I think it's very relevant, and it's good to have some programming also in our presentation, so I'm very glad that you presented that. It's very good quality. So it was the last presentation from the speakers. We have half an hour left, and I'd like to present some ideas with you about how the future could look like. So I ended the previous presentation with 3 bullet points on who do we address. And I think it's very important to bear in mind who are our users, because all of you here, you come from different backgrounds with different needs. And all together, we need to find a way to make Scilab better for everyone. I segmented in 3 parts, and some of the needs that are gathered here might not represent all of the community, but I'd like to have it as a working document with you for the future in order to slightly and iteratively take into account the most important needs so that Scilab can grow. The first point, as I mentioned, is to address traditional CA users. So CA stands for Computer-Aided Engineering. Engineers that are mainly in R&D departments of, well, rather large industrial companies, in the automotive domain, in the aeronautic domain, pretty much everywhere. And at the moment, they rely on very expert software, and they have very evolved needs. So here I took some examples, and actually the good point about looking at this population is that they have very evolved needs and that they can actually leverage some of the functionality of Scilab. The good part about being now part of ESI is that, well, we get to use Scilab, and that's actually quite great because some of those people were doing numerics, but they might not even know it. When you're doing computational fluid dynamics, for instance, you're manipulating a lot of data. It can take hours and even days to complete one single simulation. So in order to optimize all of what goes around this very precise modeling of physical phenomena, you might want to leverage different physics and different mathematics methods. One of the methods that I will be detailing a bit afterwards in this presentation is model reduction. But basically, it's just simple mathematics, the way of using all of the linear algebra in order to decompose a problem and see it through a lens that will apply relevant information for the analysis. For vibroacoustic, it's actually the same. We had a project with a client of ESI, a tier 1 of the aeronautic domain. And basically what they wanted to do is to make active noise control, so trying to reduce, just like with Bose headsets, trying to reduce actively the noise around the head of someone sitting in an airplane. So here we were facing different problems like low frequency that would come from, for instance, the nacelle. So when the nacelle is vibrating, for instance, there's some vibroacoustic signals that it's coming to our ears, and those are some elements that we want to reduce. So optimization in those cases obviously means reduction. And also high frequency, such as fans that will be in an airplane. So if you're sitting in an airplane, you can hear the fans, and those are some of the noise that you might want to reduce. Another example that we took from one of our projects this year with a tier 1 supplier of the automotive domain. It was an Indian company. They were developing a brand new electric motor engine. And basically, their problem was starting off from a finite element electromagnetic modeling and simulation. And starting from this static modeling, they wanted to optimize the design of this motor before going into production. This proved not to be feasible only with finite element modeling, because actually one single simulation would take 3 to 4 hours for one single angle of the motor. And basically they wanted to have a complete dynamic system modeling of the motor in operation. So what we performed is a system modeling based out of finite element data. And this system afterwards was deployed in order to validate with regard to the test and measurement, because obviously they wanted to make sure that all of the parameters of the design were fine-tuned before going into production. So some parameters like, for instance, the number of turns in the wire, number of poles, and so on, those were the different parameters that were needed to be optimized. So what I just want to capture through these few examples, those few examples, is the fact that now we have some interesting feedbacks from actual engineers and scientists that could be leveraging some of the capabilities of Scilab, and we want to use this in order to make Scilab better, not only in the functionality, let's say at the core, but also some functionalities in statistics, optimization, and so on. Now, the core of the problem, as it was stated, let's say at the origin of Scilab, is people performing system simulation. So what does system simulation mean? You can see it in different ways. So in the first point, I was mainly talking about everything that goes around mechanical engineering. So I'm actually a mechanical engineer myself, and well, I understand most of what is going on at ESI at the moment, but what is performed with MATLAB is mostly actually electronics. And if you would look back at the diagrams that I showed you this morning about the spread of the use of Scilab across different application fields, you will notice that mechanics is number 3, electronics is number 1. So we saw a presentation from Qualcomm. They are doing very intense so signal processing, all of the electronical design with tools that they called EDA, and it's something that is spread here. I mentioned chip design, so signal processing, and I'm actually talking about Qualcomm, but it's also something that is very well spread in the automotive. Now, there's not one single car that goes out in the market without going through the complete model-based design from, well, MATLAB Simulink in this case. But we believe, and we've seen also a very interesting example from the DLR, that there could be an alternative to that. Obviously, there are challenges, because if you remember the presentation from the German Aerospace Center, an automotive could be typically up until 15,000 blocks with 6 different levels of hierarchy and precision. So in order to design and validate a complete development, it can take a significant amount of work, and it's going to push the barrier, the frontier that Scilab and Exos have currently at the moment in terms of performance, usability, and so on. I will address that just after. And not to forget about all of the engineers and scientists that are getting new to simulation, because actually if you look at those 3 points in a matter of maturity, you can see that at the very top you have experts, people that have probably master's degrees or even PhD. For the case of CFD, it's often PhDs. For system simulation, it's gonna, I mean, it is at the moment, it's spreading. The use of system simulation, as it is encompassing different physics in a model that does not necessarily require PhD or very advanced knowledge in one field in particular. This is actually spreading. And the last point, there's more and more engineers that are learning how to program. And, well, obviously there's alternative. I'm speaking about Python, obviously, not Excel, because I don't believe that Excel is an alternative to doing good engineering work. But it could be a start. I mean, I'm not saying Excel is bad. I'm just saying that it's not always the right tool. So in the example of Sanofi, they started off, and Jean-Pierre told us earlier today about the early days of OptiClim. It reached very early the limits of what can be done with Excel, because Excel is not meant for the deployment of application. We saw the same in different process industries like with Air Liquide. And here, we want to be bringing all of the potential of simulation to as many people as possible. Those are the 3 main targets that we have in mind, and those are what we want to address for the future. So we have been for 1 year, at least. I mean, the recent year was especially intense, but we've tried to gather some feedback, to get together with the team and try to look at the axes that could be relevant for the future, where we stand out, where we see also that we don't make a difference, because at some point we need to look the reality in face. That's the fact that For instance, Python is very well developed in machine learning and data analytics. It's a fact today. There's a lot of adoption around application development, and especially in data analytics, around Python. So I think it's not relevant to compete in places where we are not relevant. We should rather try to leverage what Scilab does best and try to build bridges with other technologies where it's not the best solution. The first point is deployment of application. So as I told you through the history of the last 5 years mainly, we figured out that a lot of our users, especially in the industry, often come to a point when they want to share their know-how, and this goes through the development of what we call the application. This is what we've been focusing on for the past 3 years, I would say. And I think it's something that we will keep on developing over the years, because it's also one point where we differentiate ourselves. Now we have a strong background in cloud computing. We have our engineers that are very familiar with those technology, and I think that's something that is very valuable for the future. The second aspect is on interfacing. So you've probably seen in all of those presentations a lot of hassles, trouble around interfacing, because, well, interfacing with software like Sophie from Bertin mentioned is sometimes difficult. There's also trouble with connecting with hardware at some point. So interfacing is key. And here it's also a big part of the value proposition in engineering. MATLAB, for instance, stands out because it has a very integrated workflow from end to end, and that enables you to start with very little knowledge and get up to speed up until the deployment on the hardware sometime, when you're not even an electrical engineer. So that's actually quite amazing. And we're not saying that MATLAB is bad. And I think in some point we should inspire ourselves more from what MATLAB is doing and not trying to just be different on what does not matter. So Octave it's still I would say under investigation because we still have lots of things to figure out technically how we can leverage this. Octave is also now the help of John. He's in our team. He has a very long experience, more than 25 years, in developing an alternative to MATLAB, and I think maybe trying to be open-minded and take into account this feedback would be very valuable for the future of Scilab. And Python, well, I think, as I mentioned, Python stands out especially in data analytics. We don't know yet how to interface properly with Python, but we hope that we'll figure it out. Maybe looking at some typical use case, this is probably key. Stéphane from ArcelorMittal mentioned this morning that they were trying to leverage some of the Python models that they have built. I think it's key for them not to waste some knowledge implemented in a technology, but being able to leverage those existing models. The same from the CNES. We saw the leverage of some Java models and software that was already developed. It's very important because indeed, well, even though there was at the end one small minor, I would say, feedback or negative feedback towards the Java support in Scilab, you said, I think, and we can conclude on the fact that it's quite good, on and all. So this is for open source technology. We will look at some coupling with closed source technology, because in engineering, at the moment, not everything is open source, and I think we need to accept it also, because we cannot change everything at once. So I think it's necessary to build bridges with established workflow in the industry. Here I'm mentioning the closest technology that we have within ESI in terms of system modeling. SimulationX is based on Modelica, so it would be also a good way for us to try to leverage very established and mature software in order to build our growth around such an ecosystem. So those are the main two, let's say, line I want us to follow for the future. How does it integrate in our current situation. So we try to summarize in this graph where we come from and where we are heading. First, we believe that Scilab stands out as a robust mathematical programming language. It is robust because it has been built for over 20, 30 years now, and it's such kind of technology does not come overnight. And I think it's good to highlight that. The fact that it's a mathematical programming language, because for me, Python is not. Python is a generic not mathematic, but programming language. So we differentiate ourselves from the very essence of Scilab in this regard. Now there are questions around the language itself, because the language differed over time from the implementation, the MATLAB implementation. There are questions that we need to answer. We don't have the answer now. I'm not going to give you all of the answers today because it cannot be written in 1 year. And I mean, Scilab lived for many, many years, so I think there's a lot of things to do yet. But at least let us try to start on good basis. For Xcos, there's a very strong challenge. I think it's one of the differentiators that we have, a model-based design environment for control system. It's also one of the strong expertise from INRIA, and it's also embodied in the software itself. Not only in Xcos, because in Scilab we have also a lot of ways to model in the time and frequency domain control system, and more generally dynamic system for both continuous time and discrete time simulation. So this is very important to never forget that those are also the basis from the scientific point of view that where we are coming from. All of this is now packaged in what here I'm calling a rapid prototyping environment. There's two meanings to that. The first one is calling from the name environment. So it's an integrated development environment. Scilab is an integrated development environment for scientists and engineers. It's not only a language, it's also a software in itself. And some people, when they start to use it, they don't see the language, they see the software. And they don't even know what a language is. We had some presentation from INRA, from Jean-Claude, and I appreciate the fact that there are some academics also presenting today. Thank you for your presentation. You highlighted the fact that some engineers and scientists that don't want to program, and that's still a fear for some, and we should take it into account, because if you adopt a tool, well, you need to be able to, in this case, maybe use it in a very user-friendly way. And that's also what MATLAB succeeded in doing, somehow to abstract the language in some way so that it does not come as the first frontier for the adoption. It is also for rapid prototyping. I mentioned rapid prototyping because it's also mirroring the use of Scilab in the industry, in the research. It is mostly for preliminary design, I would say, early stages of the design, when it's about writing an algorithm and trying to find ways at a very elementary level in order to figure out the essence of your problem. So based on those pillars, those are the two new directions that we want to adopt for the future, as I mentioned, interoperability and deployment. I will try to get a bit more concrete, even though I don't want to, today, I don't want to overpromise and come with things that will not happen. I'm not going to tell you that Scilab 7 is going to be released next year, because I don't think there's a point in it. And I also think that it's something that should not come from me. I think it's something that should come from the community altogether. So now we need to revise the way we decide about the future and the whole governance. So I'm going to speak about it more in the coming slides. It's so a few ideas. Let's take it just as a few ideas. Deployment. What I would like to suggest to you is first to consider the idea of an app designer. So what could it be, an app designer? A way to improve and facilitate the development and the deployment of an application. I'm mentioning model reduction in the context of finite element simulation as a way to deploy the know-how that is built in engineering and R&D department further throughout the product lifecycle. In the environment enhancement, I think there's not much to say. Improving the integrated development environment, I'll have a slide just for that afterwards. Improving XCOS. For interoperability, interfacing, so first I mentioned the functional mockup interface. It's a standard and I think it's good for us to follow standards. Also develop a link with finite element solution, CAE solution, because I think that's one particular market niche where we could be better than MATLAB even. And maybe that's good for us to try to find a way to be in some place better than MATLAB and just not be defined with regard to MATLAB, but just say this is what Scilab is. Because now we won't be just like MATLAB, we will be Scilab. So an enhanced development environment, what could it be? So why should we develop an enhanced development environment? I would say we spent about 10 years to develop further a new language to make it more mature, more stable, better use of the memory. So Scilab 6, I think in itself is a success because of the language, but the environment did not change a bit. And maybe for 10 years, well, the world has changed a bit, so maybe you would want to have some new features on the environment itself. Also, it might be a way for us to leverage our new learned capabilities in terms of web development, web technologies. And it's also, by basing on new technologies, it might also raise the contribution from a whole new kind of engineers and contributors. So this is an idea. We want to investigate this further with you. Also, one aspect that this will cover is to facilitate the introduction of a debugger. At the moment, we have a command line debugger, GDB, and it's not integrated in the SciNot, in the editor. And the cost of implementing it in the existing editor in Java, all of the environment is currently in Java, might be higher than trying to implement on new technologies that are already taking into account such features. So this is also one of the ideas that we would have through this project, is try to integrate a new debugger. And also enable the link with Scilab Cloud, because at the moment Scilab Cloud is something that is, well, it's something that is rather for enterprise use, and maybe we can find a way to make it more available for more people. In order to do so, we might need to link it closer to the Scilab Studio, and well, we call it Studio because it's as an opposition to the cloud. So try to make a link between Scilab Studio and Scilab Cloud. So those are the few ideas. Afterwards, we can discuss on those ideas. If you already have questions, you can go ahead and interrupt me or just launch a debate. Next step would be to enhance XCOS, because I think XCOS has a very large potential. We saw it today with the use case of the German Aerospace Center. But it's something also where we have less users than Scilab. At the moment, we have quite good users of Scilab, also in the industry, but on XCOS, it's mainly used at the moment in the education. There's a lot of users in control system that are learning Scilab, learning science, learning control systems through the use of XCOS, especially in France, in preparatory classes. So I mentioned like every year there's about 30,000 of them learning Scilab, 50,000 in first year and 15,000 in second year, and it's mostly Xcos actually. So here there's three main aspects: reliability, usability, and efficiency. Reliability, well, I think it speaks for itself. We need to be able to have large diagram, to be able to scale and not crash if there's a problem. Usability is about handling all of those links. It can get messy, and it's a very difficult science to master. So here we need to find a way to put into requirement all of the feedback that are coming from user experience. And efficiency, this is a bit easier to quantify. It's in the first place about time behavior, trying to be quite fast in the simulation so that a large diagram would not take for ages to simulate. Interoperability, in this case I took the example of Simulation X. So basically, the functional mockup interface here would be a good way to interoperate with a lot of existing tools on system modeling. Even MATLAB is kind of adopting it. I mean, there are some plugins developed by third party in order to import and export a model as a functional mockup interface. I'll cover that a bit later. And last slide about the overall ecosystem, because as I mentioned, we need your help to improve Scilab. As you've seen, I mean, we cannot deny the fact that there's an economic equilibrium to find in order to have a software that will evolve further. It's not only up to ESI to decide and to act on the future of Scilab. The community needs to play a role. Without involvement from the community, there's no reason that there will be any change. So there are some things that we can do on our side, and we commit every day by our action to try to do our little bit on making Scilab better, but it's not always enough because we are a small team, as I mentioned. In the first place, what we'll try to do is to centralize all of the information that is relevant to the community. So the website, we'll try to improve it a bit because that's actually the first point of entry for every new user and also existing user of Scilab, so scilab.org. At the moment, there are two websites. I created scilab.io about 3 years ago in order to build new content around the software, but it was also to just avoid the fact that the underlying platform of scilab.org is getting quite old, and now I don't want to ignore that anymore, so we will merge the two in order to have a new, strong and stable platform sustaining scilab.org. It's basing on Drupal, and most of all, it's also it's handled by a team of professionals. It's a web team of ESI, and I believe that it's a strong commitment also from ESI to do that. I think it's mostly positive. Now it does not mean that there cannot be output. I mean, output from ESI and input from the committee, exchanges in both ways in order to improve this, because it's a new step, and we are centralizing the information because at some point I think there's no other way but having some sort of a centralization. So we'll try to make it a success. We will see next year. I hope that the adoption and that all of the information that revolves around Scilab will be more accessible and that people will be able to find it easier. Toolbox management, it's a key issue. We've highlighted many times the fact that Atoms, our platform for toolboxes, should provide up-to-date toolboxes. It's just a symptom of a larger problem. Here again, the underlying platform of Atoms is quite old, and maybe we need to do something about it. So maybe we will see with the development team and some feedback from our close partner in order to find a solution in order to make this evolve in the right direction. But here also we need help from the community. I want to thank particularly Samuel, because he has spent a lot of time and a lot of effort in order to port all of the toolboxes that were up until now on Scilab 5 in order to port it to Scilab 6. It's a huge work, and I think it's not just up to us. I think it's up to everyone. Anyone can do that, and I really appreciate the fact that some people are standing out, stepping up in order to do what is necessary. The bug report is also very important because it's also the mirror of the quality of Scilab. Scilab, as any software, when it gets older, it gets better. And it's not like the physical world. When you have more test cases, it's improving the quality of the software overall. So some of the quality and the fact that Scilab is robust comes from the Bugzilla and the bug report. And anything that the community can do in order to report bug is an improvement for the software. And community exchanges, well, I hope that today was a good platform in order for us to communicate. Well, sometimes communication in the physical world are not so easy. Maybe the mailing lists are at least providing some ways of having asynchronous ways of letting messages that other people will read and maybe answer. Maybe overall we need to find a good way to communicate. Here we are investigating some ideas, maybe a new community forum. Nothing is fixed at the moment, but I think communication is key. So if we find good ways in order to communicate, I think this is one of the essential points of the success of Scilab for the future. I have a few more slides, but actually I don't want to present them because I think it's not in those slides what will happen. I think what will happen is, well, it's still a mystery, but I hope that what will happen is built about all of the exchanges that we had today. I think it's better now to, if you want, to go to an open Q&A. If some people want to come and present something, tell something about their use of Scilab, ask something, anything, I think now is actually a must. It's a much better time than to present slides. So I'm going to stop now. So, do we have volunteers or questions? Yes, Samuel. Yes.
Is there anything planned for the graphical editor? Is it in SCL still? And is there any plan to record it in Java or
Yeah, this is a large point. So graphics in Scilab is complicated, and the problem is at the moment that we lost some part of the control in terms of competencies on this aspect. So now, graphic overall, I mean, what you're mentioning is a graphical editor because it's one part of it, but I think if we are to be successful on handling graphic properly, maybe we should not just take this part, but try to find a way to make this more sustainable. At the moment, we don't touch so much about the graphics. The last time we touched about the graphic, it was for the implementation of Scilab Cloud. It was about developing a new view in the MVC, in the model view controller architecture of the graphic. And it was actually, so we have a Java view, as you know. And now we implemented a new view, a new HTML JavaScript view in order to output something in a browser. But I think if we need to change something about the graphic, we need to rethink this, to try to find a way. Maybe at the moment, and here Clément might help me about graphic because there's a lot of Java in it. I think the model itself is also in Java, right? So yeah, there are some refactoring, some architecture work to be performed. It's also a question of do we want to take it down to smaller pieces and just address first what you mentioned, or do we want to plan it bigger, but then there's a higher risk of failure? It's a complicated question that we sometimes faced the wrong way if we look back at the history. Maybe there's just a good way to just try to port the existing TCL graphic editor in Java, and that's just a short-term action. But at the same time, it's also a question of what value does it bring and to who, in order to see how we can also finance this project, because obviously it will require some effort. So it's a question that is worth at least documenting, trying to find ways in order to express this in requirement, and see how we can also find ways to make it dependent maybe to another project where we would need it, just like the cloud. We needed the cloud, so we invested some effort. And so now that ESI is supporting the cloud, and that is something that might also bring further revenue and some positive potential of growth, then maybe we can find ways to improve the graphic at the same time. So this would probably be a way. So try to find an in-between, I would say. Try to find the right scope in order to make the graphic evolve. I hope it answers your question. Partially. Okay. Another question. Maybe I will balance and I'll come back to you. Yes? Do you want to commit to packaging and compiling Scilab regularly? It's something, I mean, sustainability is something that is difficult to comprehend for human brains, I think, because we think that thing will appear over time like this, but here with Scilab, that's the problem that we faced, is that how can we provide services to the community when at the same time we need to make sure that, well, our employer is still happy, and so that the overall thing is positive, that is not, that it's at least stable, maybe growing, but not decreasing. In the past year, the problem is that we could not commit so strongly to regular versions of Scilab because in the first place, we needed to do some of the missions on Scilab, okay, on some applications on Scilab, so not on Scilab itself, that was bringing value to only some people, but people that were paying us to do so, and so that balance the two has been challenging. So I'd rather not come and tell you, okay, we will have those release at those time, because I think it's something that I mean, it needs to come with something that a bigger plan, something that will work. So I will not tell you now when is the next release of Scilab, because right now I think it's not the right thing to do for Scilab. We need to find a way with industrial people and an ecosystem in order to build a sustainable way of producing further versions of Scilab. And eventually, I'm pretty sure that it will happen. It's working on a nightly build, isn't it?